Ever wonder how Hershey's, Maltesers, and Smarties stay so perfectly consistent when they're built in totally different ways? If they mess up one small step, entire batches can be ruined that cost millions to make. In this video, we go inside the production lines, going from molten chocolate to finished packs, catching the make or break seconds where the product becomes perfect. Hershey's milk chocolate is produced by taking dry solids that would feel gritty on the tongue, suspending them in cocoa butter and milk fat, then forcing that suspension through particle reduction, moisture stripping, and crystal control until it can be poured into molds and set into stable bars. Chocolate begins as a set of dry streams that must be kept dry. Sugar is received as granulated crystals and screened to remove clumps that resist grinding. Milk solids arrive as powders and are sieved because compacted lumps do not disperse evenly and later create specks. Cocoa solids arrive as cocoa liquor, cocoa butter, and sometimes cocoa powder, depending on the formula and plant layout. Cocoa butter is melted and filtered. Cocoa liquor is held warm, so it remains pumpable and is filtered to remove unmelted fragments. Water is kept out of all these streams because even small moisture content causes chocolate to thicken sharply. The first assembly step is a pre-mix that creates a uniform paste for refining. Melted cocoa butter and cocoa liquor create the continuous fat phase in a mixer. Sugar and milk powders are introduced gradually so they become wetted rather than forming dry islands. The mixer uses high torque and wall scraping because the mass is thick before refining. The goal is not smoothness yet, but even distribution of solids, so downstream mills see a consistent feed. Particle size reduction is then applied. Refining is performed with roll refiners or equivalent milling equipment that squeezes the paste through narrowing gaps. Each pass breaks sugar crystals and reduces the size of milk and cocoa particles. The target is a particle size below the tactile threshold on the tongue. When the chocolate reaches this range, its texture becomes smooth rather than sandy. The output of roll refining often emerges as thin flakes because the refined mass forms a film on the final roll and breaks off. Those flakes behave dry because they have huge surface area and not enough free fat coating at their surfaces. They also hold trace moisture and trapped air. If left untreated, they will make the chocolate thick and harsh. Conching is the step that fixes both flavor and flow. Conching combines heat, time, and mechanical work to coat particles fully with fat and drive off moisture. The refined flakes enter a conch where paddles knead the mass. Heat keeps cocoa butter fluid so it can spread across particle surfaces. Mechanical shear breaks down any remaining agglomerates and distributes fat uniformly. Airflow through the conch carries away moisture and volatile compounds. Moisture removal is critical because water causes particles to cling together and raises viscosity. During early conching, the chocolate may appear pasty and resistant. As conching continues, friction drops and the mass becomes more fluid and glossy. This change is the result of improved fat wetting and lower moisture. The conch is controlled to reach a defined viscosity and yield stress that matches the needs of molding equipment. Too thick, and the depositor will underfill corners and create air pockets. Too thin, and the bar edges will become heavy and the surface will be more prone to flow marks. Emulsifiers are typically added late in conching to fine-tune flow. Lecithin reduces yield stress by improving particle wetting. Additional emulsifiers can be used to further reduce viscosity at the same fat level. These additions are dosed precisely because small changes have large effects on how the chocolate runs through pumps, valves, and deposit heads. After conching, the chocolate is transferred to holding tanks with gentle agitation. Agitation prevents separation and keeps the suspension uniform. Temperature is held stable because viscosity is temperature sensitive. The chocolate is filtered again before tempering to remove any remaining lumps that could block depositor nozzles or cause surface defects in molded bars. Tempering is where the bar's final structure is engineered. Cocoa butter can crystallize in multiple forms, but only one dominant form produces the desired gloss, snap, and contraction for mold release. Tempering machines first heat the chocolate to erase existing crystal memory. They then cool the chocolate under agitation to nucleate crystals. Finally, they reheat slightly to melt unstable crystals while leaving stable seeds. The result is a chocolate that remains fluid at working temperature while carrying a controlled population of stable seed crystals. The tempered chocolate feeds molding lines. Molds are cleaned and conditioned so their surfaces are dry and at a controlled temperature. A mold that is too cold can cause premature setting and poor surface finish. A mold that is too warm can slow setting and increase smear risk. Deposit heads meter a precise mass into each cavity. Mass control is essential because bar weight is regulated and because cooling time depends on thickness. After deposit, molds pass over vibrating tables. Vibration removes trapped air bubbles and levels the surface. It also helps the chocolate flow into fine corners and embossed details. Vibration intensity is controlled because excessive vibration can create thin edges and heavy centers. The filled molds then enter a cooling tunnel. Cooling is staged to set the chocolate without creating stress or bloom. The first zone sets the surface quickly to protect shape. Later, zones cool more gradually so the interior solidifies while stable crystals grow. The chocolate contracts slightly as it cools, which creates a gap between the bar and mold wall and enables release. Cooling that is too fast can produce internal stress cracks or a dull surface. Cooling that is too slow reduces throughput and can leave soft surfaces that pick up marks. When the bars reach the release temperature, the molds are inverted or flexed and the bars drop out. Release performance is a sensitive indicator of correct temper. If temper is weak, bars cling to molds and show smeared surfaces. If temper is strong and cooling is correct, release is clean and the surface is glossy. After demolding, bars are conveyed gently to avoid scuffing. Inspection checks can identify broken corners, surface voids, and weight deviations. Bars that fail are diverted to rework streams. Reworked chocolate is remelted and returned upstream because it cannot be reintroduced directly into tempered chocolate without resetting its crystal state. Packaging begins once bars are fully set. Wrapping material is folded around each bar and sealed. Seal temperature and dwell time are controlled so film closes without heating the bar enough to soften the surface. Wrap tension is controlled to avoid imprinting. Codes are printed for traceability and packs are inspected for seal integrity. Bars are then cartoned or case packed for distribution. Maltesers are manufactured by first creating a rigid, hollow, malted honeycomb core that is mostly air, then sealing that fragile core with a thin chocolate layer, then finishing it with a stable outer chocolate coat before cooling, screening, and packaging. Everything starts with the center, because the honeycomb is not molded like a solid candy. It is created by generating gas inside a very hot sugar melt and then freezing that gas structure before it collapses. The center, therefore, needs a syrup that can foam explosively, set fast, and remain dry enough to stay crisp inside chocolate. Sugar is staged as a dry crystal feed and screened to remove clumps that can seed crystallization. Glucose syrup is held warm so it pumps smoothly and helps prevent uncontrolled graining. Malt extract or malt syrup is prepared as its own stream because it brings both flavor and solids and influences viscosity. Water is filtered and tempered because it affects dissolution and cook consistency. A small amount of fat may be included in some systems to control bubble wall brittleness, but the dominant structure comes from sugar glass. The syrup is cooked to a very high solids level. Sugar, water, glucose syrup, and malt components are dissolved and then heated rapidly in a cooker. The cook endpoint is chosen to make a glass that is brittle and sets quickly. If the syrup is too wet, the foam collapses before setting and the honeycomb becomes dense. If too dry, the melt becomes too viscous to expand evenly and can trap large irregular voids rather than a fine network. As the syrup reaches endpoint, it is transferred quickly to a mixing and aeration stage. This stage is designed to incorporate a gas-generating agent at the last moment. The syrup temperature is still high enough to keep viscosity low, but it must not be so high that the agent decomposes too early in the pipework. The gas-generating agent is introduced in a controlled dose, and the syrup is mixed just enough to distribute it without deflating the forming foam. The moment the agent reacts, gas expands through the melt and inflates it into a foam. Expansion is rapid, so the process immediately directs the foaming mass into a casting system. The foam is deposited into trays or onto a belt in a thick slab. The slab rises as gas expands, then begins to set as the melt cools and transitions into a glass. Cooling is engineered to lock the foam architecture. The outer surface must set quickly so the slab holds its height, while the interior must cool enough that bubble walls become rigid. Airflow and plate cooling are used to pull heat out without introducing humidity. Humidity control matters because a fresh honeycomb surface is hygroscopic and will become sticky if it absorbs moisture. Once the honeycomb slab reaches a cuttable brittleness, it is broken down into cores. This is not a clean slicing operation because honeycomb fractures along cell walls. The slab enters a breaker that applies controlled compression to crack it into chunks. The goal is to generate pieces that will later be rounded and sized rather than leaving long jagged shards. The breaker is tuned to minimize powder because honeycomb dust contaminates chocolate and dulls coatings. After primary break, the pieces are sized and shaped. Screening separates oversized chunks, target pieces, and fines. Oversized chunks are returned to the breaker. Fines are removed because they create dust and can clump. The target fraction moves to rounding drums that tumble pieces gently and knock off sharp spikes. Rounding improves coating coverage and reduces punctures that can rupture the chocolate film later. The honeycomb cores are extremely fragile, so conveying is designed with low drops and soft transitions. Vibrations are minimized because they generate dust and fracture. The cores are also conditioned in dry air. Conditioning equalizes temperature and reduces surface tack. It also stabilizes moisture so the cores do not soften before chocolate sealing. Before full coating, the honeycomb is usually sealed. Sealing is a thin chocolate or compound layer that penetrates slightly into surface pores and blocks moisture transfer. Without sealing, the honeycomb would absorb moisture from the chocolate environment and later from the package headspace, losing crispness. Sealing, therefore, acts as a barrier layer and a structural reinforcement. Sealing chocolate is prepared and held at a viscosity that can wet porous surfaces without flooding them. If real chocolate is used, tempering is applied so the seal sets quickly and remains stable. If a compound coating is used, temperature control sets viscosity and set speed. The cores enter a pre-coat stage where they are tumbled while a fine chocolate spray is applied. The spray is light and repeated in several passes because a heavy single application would collapse the honeycomb edges and create thick, uneven spots. After sealing, the cores pass through a short cooling tunnel to set the thin layer. Cooling is tuned to harden the surface while keeping the core dry. Once sealed, the cores can survive the more aggressive motion of full enrobing or panning. The final chocolate coating is applied either by enrobing with a curtain or by panning in rotating drums, depending on the line design. For Maltesers style spheres, panning is often used because it builds an even coat around irregular cores. The sealed centers are loaded into rotating drums, and a measured amount of chocolate is applied in stages. Each stage adds a thin film, and then cooling air sets it before the next film is applied. This staged build prevents the weight of wet chocolate from deforming the fragile centers and prevents pieces from sticking together. Chocolate viscosity and temperature are controlled tightly during coating. Too warm and chocolate becomes thin, runs and pools, leaving uneven thickness. Too cool and chocolate thickens, builds rough surfaces, and fails to flow into small contours. If real chocolate is used, temper control is critical because the coating must set with stable crystals to resist bloom and to provide a clean snap. The coating system therefore monitors temperature and flow resistance and adjusts cooling and heating to keep chocolate in the working range. As coating thickness builds, the process focuses on surface smoothness. Early layers are allowed to penetrate and lock onto the sealed surface. Later layers are applied in thinner films with longer setting time to reduce texture. Drum speed is tuned so pieces roll rather than slide. Rolling distributes chocolate evenly and prevents flats. Sliding creates thin spots and scuffs. Once the coating reaches target thickness, pieces enter a final cooling tunnel. Cooling is staged to avoid stress cracks. The outer surface is set first to protect shape. The interior of the chocolate coat is then cooled gradually so crystals stabilize. Stable cooling also prevents condensation. Condensation causes sugar bloom and surface haze, which is especially visible on smooth chocolate spheres. After cooling, pieces are screened to remove doubles and broken cores. Doubles occur when two pieces stick during a wet stage. Broken pieces shed honeycomb dust and compromise appearance. Screening uses mesh decks sized to the product diameter band. Off-size pieces are diverted. Quality checks focus on core crispness and coating integrity. Crispness is influenced by honeycomb moisture and by seal coverage. Coating integrity is influenced by chocolate temper and cooling. Weight checks confirm coat thickness and core mass remain stable. Visual inspection can detect flat spots and scuffs that indicate coating issues. Packaging begins only after pieces are fully set and at a stable temperature. Warm chocolate will mark and also may release aroma components differently. The pieces are conveyed gently into multi-head weighers. Flow is aided by the spherical shape, but fines can still cause bridging, so dust control remains important. The weigher portions target weights by combining small hopper dumps. Portions drop into bags formed on vertical form-fill seal machines or into cartons depending on format. Seal timing is tuned so chocolate pieces do not lodge in the seal area. Seal integrity matters because moisture ingress will soften honeycomb through the chocolate over time. Packaging films are selected for moisture barrier performance because protecting core crispness is the main shelf life requirement. Case packing and palletizing are designed to limit crushing and temperature swings. Excess vibration creates scuffs. Temperature spikes can soften chocolate and accelerate bloom risk. Stable storage conditions help maintain coating gloss and keep the honeycomb core dry and crisp. The crunch of a Smarties shell is not an accident. It is built one microlayer at a time until a measured thickness of crystalline sugar surrounds a chocolate core and behaves like a small engineered capsule. The process begins by defining the target finished diameter and shell thickness, because those two numbers determine everything else. Once the shell target is set, the center must be manufactured to a diameter band that leaves enough room for the shell to grow without producing oversized pieces. That means the chocolate core is treated as a precision pellet rather than a simple molded chocolate. Chocolate preparation starts with creating a stable suspension of solids in fat. Cocoa components, sugar, and milk solids are blended so powders are evenly distributed. Refining reduces particle size so the chocolate is smooth and so the core surface is dense rather than crumbly. Conching follows to complete fat wetting and remove residual moisture, because moisture would later cause texture defects in the shell build. The chocolate is then tempered, so cocoa butter forms stable crystals. Temper stability matters here because the core will be tumbled for long periods in rotating pans, and a poorly crystallized core would soften and flatten under repeated impacts. Core shaping is done to achieve a lens profile that rolls predictably. The chocolate is metered in small doses, either into shallow cavities or onto a cooled surface where it can be shaped. Metering controls mass tightly, so core weight distribution stays narrow. Shaping controls curvature, so the piece does not develop a flat face. Flat faces roll differently and receive shell build unevenly. After shaping, cores are cooled in staged tunnels, so they harden without cracking, and so their surface remains dry and non-tacky. Before shell building, cores are conditioned. Conditioning brings the cores to a temperature where they are hard enough to resist dents, but not so cold that their rims chip and create sharp edges. Rim chipping is a problem because chips become weak points where shells later crack. Conditioning also prevents condensation because any surface moisture would dissolve the first sugar layers and create rough, orange peel textures. Shell building is carried out in rotating pans or perforated coating drums. The cores enter as a rolling bed that must remain in a consistent cascade. Drum fill level and rotational speed are set to create rolling contact rather than sliding. Rolling ensures all surfaces are exposed evenly to syrup and air. Sliding causes flat spots and uneven thickness. The mechanical motion is therefore treated as a controlled input in the same way as syrup concentration. The first shell layers are designed as a bonding bridge. A light syrup is atomized into very fine droplets and sprayed in short pulses. Droplet size is kept small so it spreads thinly and does not pool. Immediately after each pulse, drying air flows through the bed and removes water, so a crystalline film forms at the surface. This early stage must be fast setting to prevent pieces from sticking together and forming twins. It must also be gentle enough not to soften the chocolate core. Once adhesion is established, the process switches to thickness build cycles. A higher solid syrup is applied, then fine sugar is introduced as a dust. The dust absorbs moisture from the syrup film and accelerates crystallization. Drying air then removes remaining water and strengthens the new layer. This spray dust dry sequence is repeated many times. Each individual layer is thin because thin layers crystallize more evenly and reduce internal stress. Thick layers dry unevenly and create trapped moisture pockets that later pit or crack. Drying conditions are tuned continuously. Air temperature must be high enough to evaporate water efficiently, but not so high that it warms the chocolate core and risks deformation. Air humidity must remain low enough to pull moisture out, but not so low that the surface hardens instantly and traps water inside the shell. The process balances these factors, so crystallization progresses through the layer thickness rather than forming a hardened skin on top of a damp interior. As the shell thickens, the sound and motion of the bed change. Pieces become harder and collision noise becomes sharper. The process compensates by adjusting drum speed slightly to maintain rolling without excessive impact. Too much impact at this stage chips edges and creates exposed shell layers. Too little impact produces irregular shapes and non-uniform thickness. Near the target thickness, the focus shifts to smoothing. Dust addition is reduced because dust tends to leave a rough micro texture. Instead, thinner syrup films are sprayed and given longer drying time. Thin films flow into micro valleys and reduce ridges created during bulk build. This is also where roundness improves because mild abrasion during tumbling knocks down high points and helps the shell approach an even curvature. Color application is treated as a separate operation, layered on top of the structural shell. Color solutions are prepared to precise concentration and filtered to remove undissolved particles that could create specks. Color is applied in multiple light coats rather than one heavy coat. A light coat wets the surface uniformly and dries quickly without pooling. Pooling creates blotches and uneven shade. Between coats, drying air sets the film completely so the next coat does not dissolve the previous one. Color is typically introduced when the shell has reached most of its thickness but still has enough surface receptivity for good adhesion. Introducing color too early risks burying pigment under later clear layers and muting shade. Introducing color too late risks weak adhesion and rub-off because the surface can be too hard and slick. The process therefore schedules color passes within a window where the surface still accepts thin films, but the shell is strong enough to tolerate extra handling. Because multiple colors are produced, color runs are separated to prevent cross tint. Spray lines are flushed between colors and pans are cleaned so residue does not contaminate the next batch. Shade is checked with optical measurement and adjusted by adding additional light passes or altering concentration within a narrow range. Uniform shade depends on maintaining consistent bed motion and consistent droplet size because any change in wetting pattern shows as streaks. After color, a protective finish layer is applied. This can be a clear syrup coat that locks pigment and reduces rub-off. The clear coat is applied sparingly to avoid creating a sticky surface. It is followed by extended drying so moisture reaches a stable endpoint. Moisture endpoint determines both crunch and handling. Too much moisture makes shells tacky and prone to scuffing. Too little moisture makes shells brittle and prone to chipping during conveying. Moisture equalization follows drying. Even when the surface feels dry, the inner shell can retain slightly different moisture. Equalization holds the candies in controlled air so gradients flatten. This reduces internal stress that can cause fine hairline cracks and improves shelf stability. Polishing is the final surface engineering step. A very small amount of polishing agent is misted into a polishing pan while pieces tumble gently. The film spreads across the shell's surface and fills micro pores, increasing gloss and reducing friction. Reduced friction improves flow through hoppers and reduces scuffing in packaging. Polishing is controlled carefully because excess polish can feel waxy and can reduce the crisp sensory perception of the shell. If a printed mark is used, it is applied after the surface is smooth and dry. Printing uses edible ink transferred by a pad system. Pieces are fed and oriented so a stable face is presented. The pad picks up ink from an etched plate and stamps it onto the shell. Ink viscosity and pad pressure are tuned so the mark is crisp without smearing. A short drying stage sets the ink before pieces are mixed and conveyed. Sorting and sizing occur before packaging. Screens remove fines and broken fragments. Optical sorting removes twins, chipped shells, and off-color pieces. Size classification removes pieces outside the diameter band because off-size pieces disrupt appearance and affect weigher accuracy. Sorting also protects packaging because irregular pieces can bridge or jam. Conveying is designed to minimize impact. Drop heights are kept low and chutes are smooth and curved. Hoppers are steep and low friction to maintain flow without heavy vibration. Excess vibration increases abrasion and creates dust that dulls gloss and contaminates seals. Packaging starts with portioning. Multi-head weighers distribute candies into multiple hoppers and select combinations that meet the target weight precisely. Accurate portioning depends on consistent piece size and free flow. The portion drops into a bag formed by a vertical form-fill seal machine or into a carton fill funnel depending on format. Seals are made while keeping candies away from the seal zone because trapped pieces or sugar dust can create leaks. The Snickers process is organized around synchronization. because nougat sets by cooling, caramel sets by concentration and cooling. Peanuts must be applied while the caramel surface is at the right tack, and chocolate must be tempered so it locks into a stable crystal form. Each stream, therefore, has its own preparation and holding system, and the assembly belt is timed so every stream meets the slab within a narrow temperature window. Nougat begins as an aerated structure that must remain stable through cutting and enrobing. A cooked syrup stream provides the solid backbone. Sugar and glucose syrup are metered and concentrated to a target solids level in a cooker. The cook is run to a defined endpoint because solids control the final resilience. Too much water leaves a weak slab that deforms under knives. Too little water yields a tight chew that resists cutting and can fracture at edges. The syrup leaves the cooker and is conditioned to a blending temperature that supports foam locking without scorching. A separate foaming stream is generated from a protein solution. The solution is mixed to a consistent concentration and fed into a continuous aerator. Air is metered into the aerator, and shear is used to create fine bubbles. Bubble size distribution is controlled because it determines uniform bite and density stability. Density is monitored continuously because density becomes the direct control for final bar weight and mouthfeel. The syrup and foam merge in a continuous mixer designed for folding rather than beating. Folding distributes hot syrup through the foam while preserving the bubble network. Heat partially sets the protein films around bubbles and increases structural strength. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be dosed to stabilize the air-fat sugar system and to control viscosity at the depositor. The mixed nougat exits warm and plastic with a defined density. Nougat deposition converts this aerated mass into a continuous slab. The depositor lays down a wide band onto a moving belt. A leveling station sets thickness. Thickness control is critical because it defines the core height and impacts later coating ratio. The slab enters a staged cooling tunnel. Early zones remove heat enough to support the next layer without collapse. Later zones firm the interior without creating a hard skin that could crack during cutting. The slab leaves cooling firm, but still slightly compliant, so it bonds to caramel. Caramel is prepared in parallel as a high solids elastic layer. Sugar and glucose syrup are cooked with milk components to develop flavor and reach a targeted solids endpoint. This endpoint determines whether the caramel behaves as a cohesive sheet or as a smear. Fat is added to smooth the matrix and reduce stickiness at knives. The caramel is cooled to a working temperature where it can be deposited as a continuous layer without running. It is held in jacketed tanks with gentle agitation to prevent a surface skin and to keep temperature uniform. Peanuts are prepared as a dry size graded topping stream. Roasted peanuts are screened to remove fines and broken bits. Size distribution is tightened so surface coverage is consistent and peaks are limited. Tall peaks create coating thin spots in the chocolate curtain. Peanuts are cooled after roasting so they do not warm the caramel surface and reduce tack control. The nut stream is held dry so it remains free-flowing at the spreader. Layering starts when the nougat slab reaches the caramel station. Caramel is applied as a continuous sheet using a slot depositor or ribbon head. A smoothing bar spreads the caramel and locks thickness. The temperature relationship between nougat and caramel is controlled. The nougat surface must be stable enough to carry the caramel without compressing. The caramel must be warm enough to wet the nougat surface and bond. If caramel is too hot, it can melt the nougat surface and create a weak interface. If too cool, it can sit on top and delaminate later. Nut application happens immediately after caramel deposition. A spreader distributes peanuts across the width in a controlled mass flow. the peanuts land on a caramel surface that is still tacky enough to hold them. A light pressing station can embed peanuts slightly to improve mechanical lock. Pressing is carefully limited so it does not crush nuts into fragments and does not force caramel to squeeze sideways. The layered slab then passes through a conditioning zone. This zone firms the caramel surface and stabilizes nut position before cutting. Cooling is staged to avoid stress between nougat and caramel because the two layers contract differently. The slab must reach a firmness that cuts cleanly. If too warm, caramel smears and drags. If too cold, caramel can crack around nuts and create weak zones under the chocolate. Edge trimming removes uneven slab edges. Trim is collected for controlled rework streams based on moisture and temperature. The main slab enters a lane cutter that slices it into long ropes. Rope width defines final bar width. A cross cutter then slices ropes into bar lengths. Cut timing is synchronized to belt speed to keep bar mass consistent. Knife surfaces are managed because caramel and nut fragments can build up and create ragged cuts. Clean cuts reduce exposed crumb that would contaminate the chocolate system. Bar centers are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfer points minimize drop height because impact can dislodge peanuts and can dent the nougat. A brief pre-chill can be used to stiffen the surface and improve chocolate flow behavior. The pre-chill is balanced so it does not cause condensation when entering the chocolate area. Chocolate coating is produced and tempered in a dedicated loop. Chocolate is melted and filtered. Tempering then creates stable cocoa butter seed crystals through controlled cooling and reheating. Working temperature is held in a narrow band, so viscosity remains stable at the curtain. Viscosity control is essential because it sets coating thickness and therefore final weight and bite. Enrobing applies chocolate as a curtain over the top and sides with a bottoming system for the underside. Bars pass under the curtain on a wire belt. Excess drains through the belt. Air knives remove excess and shape the surface. Air knife settings are tuned to avoid exposing nut peaks at corners while still controlling the foot at the base. A stable curtain and consistent belt speed keep coating uniform across the run. If a surface pattern is required, it is added while the coating remains tacky. A stringer drizzles thin lines that bond to the base coat. The bars then enter the cooling tunnel immediately. Cooling is staged to set the chocolate without stress and to lock nuts into the coating. The first zone sets the surface quickly so the coat does not slump and so peanuts stop shifting. Later zones cool more gradually to promote stable crystal growth and reduce bloom risk. Tunnel humidity is controlled to prevent condensation and surface haze. Bars exit cooling at a temperature where the chocolate is hard enough for wrapping without scuffing. Inspection follows cooling. Vision systems detect exposed edges, bald spots, and coating splits. Weight checks confirm portion control across cutting and enrobing. Bars outside tolerance are diverted. Chocolate rework is remelted and returned upstream, while nougat and caramel rework streams are handled separately because their aeration and moisture differ from fresh mass. Wrapping begins with a flow wrapper that forms film around each bar and seals it. Seal temperature and dwell are tuned, so seals are tight without overheating the chocolate. Film tension is controlled to avoid scuffing. Code printing adds lot and date marks. Wrapped bars are then collated into multi-packs or cartons and case packed. Bounty bars are manufactured by turning desiccated coconut into a cohesive moist center with a controlled chew, shaping that center into bars, sealing it with tempered chocolate, then cooling and wrapping while moisture and fat migration are kept stable. The production logic starts with coconut water management because the center is engineered to feel moist without releasing liquid into the chocolate coat. The plant therefore treats coconut solids, sugar syrup, and fats as a binding system that must land in a narrow water activity window. Desiccated coconut arrives as a dry particulate with variable flake size. It is screened to remove fines and oversized pieces. Fines can make the center pasty and reduce the fibrous bite. Oversized pieces can tear through the chocolate coat and create weak points. The coconut is conditioned in controlled humidity storage so it does not pick up moisture unevenly, because uneven moisture produces streaks in center firmness. Sugar syrup is prepared in parallel. Granulated sugar is dissolved in heated tanks with agitation until the solution is clear. Glucose syrup can be added to control crystallization and to keep the center from becoming gritty. Syrup concentration is controlled by density. Too dilute a syrup makes the center wet and prone to weeping. Too concentrated a syrup makes the center dry and crumbly after cooling. A fat stream is prepared to chew and to carry flavor. Vegetable fat is melted and held at a defined temperature, so viscosity is stable for metering. Emulsifiers can be staged to help distribute fat through the syrup and to improve binding to coconut fibers. Flavor. Additions are prepared as concentrates that can be injected late, so aroma remains strong. Center mixing begins by building a binder phase. Warm syrup and melted fat are blended into a uniform liquid. The blend temperature is chosen so the binder wets coconut quickly but does not cook it. If the binder is too hot, it can soften coconut structure and reduce bite. If too cool, it thickens and coats poorly, leaving dry coconut pockets. Coconut is then introduced into the binder in a high-torque mixer. The mixer uses folding action to pull coconut through the binder and coat every particle. Mixing energy is tuned to avoid shredding coconut flakes into fines. The mass transitions from loose dry flakes to a cohesive, moist mixture as syrup fills voids and fat coats fibers. The endpoint is judged by uniform gloss and consistent torque with no visible dry streaks. Moisture control is enforced at this stage by controlling binder ratio and mixing residence time. Coconut absorbs binder and then slowly releases free syrup if overloaded. The line, therefore, targets a ratio where the mixture holds shape when compressed but does not bleed liquid. This stability matters because free syrup would dissolve sugar at the chocolate interface and cause separation later. Once mixed, the coconut mass is conditioned. Conditioning equalizes temperature and allows binder to distribute through the fiber network. It also lets any entrained air rise out. Air pockets are undesirable because they create voids that collapse during enrobing and cause dents in the coating. Conditioning is often done in a feed hopper with gentle agitation to keep the mass uniform while avoiding further breakdown of flakes. Forming converts the coconut mass into bar centers. A common method uses extrusion. The mass is fed into an extruder that compresses it and pushes it through a rectangular die. Compression removes air and densifies the center to a consistent bulk density. Die dimensions set width and height. Belt. Speed is synchronized with extrusion output to prevent stretching because stretching changes density and later chocolate ratio. As the extruded ribbon exits the die, it enters a cutting station. A guillotine or rotary knife cuts the ribbon into bar lengths. Cut timing is locked to belt speed to maintain consistent weight. Knife geometry is designed to slice cleanly through fibrous coconut without dragging. If the mass is too warm, it smears at the cut. If too cool, it fractures and sheds crumbs. The line holds a narrow temperature window to produce clean edges. Some formats form the center by compression molding rather than extrusion. In that route, the coconut mix is portioned and pressed into cavities. Pressing controls density and surface smoothness. The pressed pieces release and move to coating. The process goal remains the same. The center must be dimensionally stable and consistent in moisture. Before chocolate coating, the centers are preconditioned. preconditioning firms the surface so it resists deformation under the chocolate curtain. It also stabilizes surface moisture so the chocolate bonds without encountering wet spots. Cooling air is controlled because overly cold centers can cause condensation, and that moisture will create bloom or adhesion defects. Chocolate coating is prepared in a separate tempering loop. Chocolate is melted and filtered. Tempering creates stable cocoa butter seed crystals through controlled cooling and reheating. Working temperature is maintained tightly because viscosity determines coating thickness and because temper drift causes bloom and weak snap. Coating viscosity is adjusted by temperature control and by cocoa butter balance. Enrobing applies chocolate to the coconut centers. Centers pass through a chocolate curtain that coats the top and sides. A bottoming system coats the underside so the center is fully sealed. Excess chocolate drains through a wire belt. Air knives shape the coat and control the foot. Air knife. Settings are tuned to avoid exposing coconut fibers at corners. Exposed fibers wick moisture and can trigger surface defects. Because coconut centers can shed fine particles, crumb management is integrated into the enrober. Centers are screened or air cleaned before coating to remove loose coconut dust. The chocolate loop uses filtration to remove any carried particles that would create specks or roughness. Stable filtration prevents buildup that would change curtain quality. After enrobing the bars, enter a cooling tunnel. Cooling is staged to set the chocolate surface quickly and then crystallize the interior of the coat gradually. Rapid surface set prevents slumping and preserves bar shape. Gradual cooling reduces internal stress and reduces bloom risk. Tunnel humidity is controlled to prevent condensation because condensation causes sugar bloom and dullness. While the coat sets, the coconut center continues to equilibrate. The binder fat begins to crystallize and locks chew. Moisture distribution stabilizes across the center. The chocolate coat becomes a barrier that slows moisture exchange. The interface between center and coat is sensitive to fat migration. If the center fat is too mobile, it can migrate into the chocolate and soften it. The formulation and the cooling profile are therefore tuned so center fat is solid enough at storage temperature to remain in place. If the product includes a decorative chocolate drizzle, it is applied immediately after enrobing while the base coat is still tacky. A stringer deposits thin lines across the top. The bars then enter the cooling tunnel, so both layers crystallize together. Inspection follows cooling. Vision systems check for exposed corners and coating voids. Weight checks confirm portion control across forming and coating. Bars with dents or broken corners are rejected. Rework handling is separated for chocolate and for coconut center. Chocolate rework is remelted and retempered. Coconut center rework is blended back only within controlled ratios because moisture and density can differ from fresh mix. Wrapping begins once bars reach a stable handling temperature. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are tuned, so the seals are strong without heating the chocolate enough to scuff. Film tension is controlled so it does not abrade the chocolate surface. Print registration aligns graphics. Date coding is applied for traceability. Wrapped bars are collated into multipacks or cartons depending on format. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case packed and palletized. Mars bars are manufactured by building an aerated nougat foundation, laying down a caramel layer that bonds without smearing, coating the assembled centers in tempered chocolate, then cooling and wrapping once all layers reach stable handling strength. The line is designed around rheology transitions rather than ingredients. Nougat begins as a warm foam that must become a cuttable slab. Caramel begins as a hot, elastic melt that must become a clean sheet. Chocolate begins as a fluid suspension that must crystallize into a stable shell. Each stage is managed by temperature windows and residence times that keep those transitions repeatable. Nougat construction starts with a syrup that defines solids and elasticity. Sugar and glucose syrup are metered into a cooker and concentrated to a target solids level. The cook is short and controlled because long exposure deepens color and shifts viscosity. Solids endpoint controls whether the final nougat feels light or tight. A syrup that is too wet yields a center that compresses and deforms under cutting. A syrup that is too dry yields a center that becomes chewy and resistant. A separate aeration stream provides the bubble network. A protein solution is mixed to a defined concentration and fed into a continuous aerator. Airflow is metered and rotor speed sets bubble size distribution. Density control is continuous because density directly determines bar weight and perceived lightness. Fine uniform bubbles are preferred because they resist collapse and create a smooth bite. The hot syrup stream merges with the foam stream in a continuous folding mixer. Folding is used to distribute syrup without shredding bubbles. Syrup heat strengthens the bubble walls and helps lock the structure. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be introduced to improve stability and to tune flow at the depositor. If a chocolate note is required in the nougat, cocoa components are added in a way that avoids sudden viscosity spikes, often by dispersing them into a small fat stream before injection. The aerated nougat leaves the mixer as a warm plastic mass with controlled density. It is deposited onto a moving belt as a wide slab. A spreader head and gauge rollers set thickness tightly. Thickness matters because it defines the bar cross-section and affects cooling time. The slab moves through a cooling tunnel with staged zones. The early zones firm the surface so it can accept the next layer without collapsing. The later zones pull heat out more gradually, so the interior sets without creating a brittle skin. Caramel production runs in parallel with a different set of constraints. Caramel is cooked from sugar, glucose syrup, and dairy components to an elastic solids endpoint. That endpoint is chosen so the caramel forms a sheet and cuts cleanly. Too low solids yield smear and squeeze. Too high solids yields cracking and glassy bite. Fat is added to smooth texture and reduce tack on knives. The finished caramel is cooled to a working temperature where viscosity is stable. It is held in jacketed tanks with gentle agitation to prevent a surface skin and keep the temperature uniform across the run. Layering is where the two streams must meet in the right state. The nougat slab enters the caramel station at a temperature that is firm but receptive. Caramel is deposited as a continuous layer using a slot head or ribbon head. A leveling bar spreads the caramel to a consistent thickness. The temperature difference between caramel and nougat is controlled so the interface bonds without melting the nougat surface. If caramel is too hot, it can soften the nougat and create a weak interface. If caramel is too cool, it can sit on top and separate during cutting. After layering, the slab is conditioned again. This conditioning step firms the caramel so it becomes cut stable. Cooling is staged to avoid differential contraction between layers. Differential contraction can create curl or separation lines. The target exit condition is a slab that holds shape, has a firm caramel surface, and can pass through knives without drag. Edge trimming removes slab edges where thickness variation is most likely. The trimmed material is collected for controlled rework streams. The main slab is then cut into lanes with rotary knives. Lane width sets bar width. A crosscutter slices each lane into bar lengths. Cut timing is synchronized with belt speed to control weight. Knife temperature and surface finish are managed because caramel can adhere and cause tearing. Clean cutting reduces exposed nougat pores that can trap air and later create coating voids. The cut centers are transferred onto the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfer points minimize drop height because nougat can dent and caramel can shear. A short pre-chill can be used to firm the surface and improve coating behavior. Pre-chill is balanced so the center does not become so cold that condensation forms when it enters the chocolate area. Chocolate coating is prepared in a tempering loop. Chocolate is melted and filtered. Tempering creates stable cocoa butter seed crystals by controlled cooling and reheating. Working temperature is held tightly because viscosity defines curtain thickness and final coating mass. If viscosity rises, the bars gain weight and corners can become bulky. If viscosity drops, the bars can show thin spots and exposed edges. In robing coats, the bars using a top curtain and a bottoming system. Bars pass through the curtain on a wire belt. The underside is coated by a chocolate bath or roller that lays a continuous base. Excess chocolate drains away. Air knives smooth the surface and define the foot. Air knife settings are tuned to remove excess without exposing corners, especially where caramel edges can create sharp transitions. A stable curtain requires steady chocolate temperature and steady pump flow. If a surface pattern is required, a stringer applies chocolate lines while the base coat remains tacky. The pattern must bond and then set without smearing. The bars then enter the cooling tunnel immediately. Cooling sets the chocolate and stabilizes the whole bar. The first zone sets the surface quickly so the coating does not slump, and so the bar can be handled. The next zones cool gradually, so stable crystals form and bloom risk is reduced. Tunnel humidity is controlled to prevent condensation. Exit temperature is chosen so the coating is hard enough for wrapping without scuffing. During cooling, the internal layers equilibrate. Nougat firms further as fats crystallize and bubble walls become more rigid. Caramel reaches its final elastic state. The chocolate coat becomes a barrier that slows moisture exchange and protects texture through storage. Inspection occurs after cooling. Vision systems check for coating voids and exposed edges. Weight checks confirm that cutting and coating remain stable. Bars outside tolerance are diverted. Chocolate rework is remelted and retempered. Nougat and caramel rework streams are managed separately because aeration and moisture history affect how they behave if recycled. Wrapping begins once bars are stable. Flow wrappers form film around each bar and heat seal it. Seal temperature and dwell time are tuned, so seals are strong without heating the chocolate enough to mark. Film tension is controlled, so it does not abrade the surface. Print registration aligns graphics and coding adds lot information. Wrapped bars are collated into multi-packs or cartons, then case-packed and palletized. Handling downstream is designed to avoid warm zones that soften chocolate and to avoid vibration that scuffs wrappers. Cadbury Dairy Milk is manufactured by transforming milk and sugar and cocoa into a low-moisture chocolate crumb or chocolate mass, refining it into a smooth suspension, conching it to stabilize flow, tempering it to lock stable cocoa butter crystals, then molding and packing while temperature and viscosity stay tightly controlled. Milk handling is treated as a structural step rather than a flavor step because dairy solids determine body and sweetness balance. Milk can enter as liquid milk, concentrated milk, or milk powder depending on plant design. Liquid streams are filtered and held at controlled temperature for predictable pumping. Powder streams are sieved to remove clods because clods do not hydrate evenly and later create texture specks. Sugar is screened to control crystal size and to remove lumps that would resist refining. Cocoa components are prepared as cocoa liquor and cocoa butter streams held warm so they remain pumpable. Cocoa powder streams are sifted when used to remove compaction lumps. All dry ingredients are kept low in moisture because water in chocolate causes thickening and unstable flow. A key feature of many milk chocolate lines in this style is crumb production, which converts milk and sugar into a dry solid that carries developed dairy notes and improves process stability. Crumb production starts by combining milk and sugar in a cooker. The mixture is heated while being mixed, so sugar dissolves and water begins to evaporate. Heating is controlled to drive off water without scorching milk solids. As water leaves, the mixture becomes thicker and begins to form granular solids. The cook continues until the mass becomes a dry or semi-dry crumb with low residual moisture. During crumb cooking, thermal history is tightly managed because it controls flavor development and functional behavior. Too gentle a cook leaves high moisture and produces crumb that later thickens the chocolate unpredictably. Too aggressive a cook darkens sugars and drives strong cooked notes that can overwhelm the profile. The endpoint is set by moisture content, and by the way, the crumb fractures when broken. When the endpoint is reached, the crumb is cooled and milled into a manageable size so it can be blended uniformly later. Cocoa liquor and cocoa butter are prepared in parallel. Cocoa liquor is held warm so it stays fluid and is filtered to remove solid lumps. Cocoa butter is melted in jacketed tanks and filtered for clean metering. These fat streams define the continuous phase of the final chocolate, and they also control viscosity through the downstream steps. Mixing combines crumb with cocoa liquor, cocoa butter, and additional sugar or milk solids as required by the recipe. The goal is to create a homogeneous pre-mass where solids are evenly distributed in fat. Mixing is done in high-torque mixers with wall scraping because the mass can be thick before refining. The mixture transitions into a paste with consistent color and no dry pockets. At this stage, the mass is not yet smooth. Sugar crystals and crumb particles are still large enough to be detected on the tongue. Refining is performed to reduce particle size. The pre-mass is fed to roll refiners or other milling systems. In roll refining, the mass passes through a series of rolls with decreasing gaps. Each pass squeezes and shears particles smaller. The refined output leaves the last roll as a thin film that breaks into flakes. These flakes have high surface area and must be processed into conching quickly to prevent moisture pickup. Conching is the step that transforms refined flakes into a smooth flowing chocolate with stable flavor. The flakes enter a conche where mechanical work coats each particle with fat and breaks down remaining agglomerates. Heat keeps cocoa butter fluid and supports moisture removal. Airflow through the conche carries away moisture and volatile compounds. Moisture removal is essential because even small amounts of water cause chocolate to seize and become thick. Conching also stabilizes rheology by reducing friction between particles. Early in conching, the mass can be dry and pasty. As fat distribution improves, the mass becomes smoother and viscosity drops. The concha profile is tuned to reach a target viscosity for molding and enrobing while maintaining the desired flavor. Over-conching can reduce throughput and strip some volatile character. Under-conching leaves high viscosity and inconsistent snap. Emulsifiers are typically added near the end of conching. Lecithin improves particle wetting and reduces yield stress. Another flow modifier can be used to reduce viscosity further at a given fat level. These additives are dosed precisely because small changes alter how chocolate behaves in deposit heads and tempering machines. The chocolate is then filtered and transferred to holding tanks with gentle agitation to keep the suspension uniform. Tempering is the controlled crystallization of cocoa butter that gives dairy milk its stable set and gloss. Chocolate is first heated to melt existing crystals fully. It is then cooled under agitation so new crystals form. It is then reheated slightly to melt unstable forms while keeping stable seed crystals. The output chocolate contains a controlled population of stable crystals and remains fluid at the working temperature. Temper is monitored continuously because it drives mold release and surface quality. If temper is too low, the chocolate sets slowly and releases poorly and can bloom later. If temper is too high, viscosity rises and the chocolate becomes thick, causing poor mold, fill and thick edges. Tempering machines adjust cooling and heating in small increments to maintain the target crystal content. Molding shapes the chocolate into bars and blocks. Polycarbonate molds are cleaned and pre-warmed to prevent condensation. Depositors meter chocolate into each cavity with tight mass control. The filled molds pass over vibrating tables. Vibration removes trapped air bubbles and levels the surface. It also improves detail in any embossed features. Cooling tunnels set the molded chocolate. Cooling is staged to set the surface quickly without creating internal stress. The chocolate contracts slightly as it cools, which helps demolding. If cooling is too fast, the chocolate can crack or warp. If too slow, the line speed drops and molds remain occupied. Cooling also must avoid condensation because moisture on the surface can cause sugar bloom. After cooling, the molds are inverted and the bars release. Release depends on correct temper and correct cooling because the bar must contract away from the mold wall. Bars transfer to conveyors where they are inspected for surface defects. Weight checks confirm deposit accuracy. Bars with defects are diverted for rework. Rework is remelted and returned upstream in controlled ratios so it does not destabilize tempering. If the product includes inclusions or filled formats, the molding stage expands. Inclusions such as nuts are screened and kept dry. They can be placed into molds before chocolate deposition or blended into chocolate with controlled suspension. Filled formats use sequential depositing. A shell is deposited and partially set. A filling is dosed and then sealed with a chocolate back layer. Cooling profiles are adjusted because fillings change heat transfer and can insulate. After demolding, bars move to wrapping. Wrapping protects chocolate from oxygen, moisture, and abrasion. Bars are indexed into wrapping machines that fold foil or film around each bar. Fold geometry is controlled so edges are crisp and seals are tight. If an inner foil and outer paper wrap are used, the foil provides the barrier and the paper provides stiffness and print. Heat sealing or crimping forms the closure, depending on wrap type. Coded information is applied during wrapping or immediately after. Vision systems check wrapper alignment and seal integrity. Check weighers verify pack weight. Wrapped bars are then collated into cartons if needed. Cartons are erected and filled with a defined count. Cartons are closed and glued. Finished units are case packed and palletized. The process control backbone for dairy milk is moisture management and particle size management and crystal state management. Crumb production drives moisture down and creates a stable dairy sugar matrix. Refining drives particle size down for smoothness. Conching drives off remaining moisture and stabilizes flow by coating particles with fat. Tempering builds the correct crystal population for gloss and snap and clean mold release. Cooling locks the structure and wrapping protects it from temperature swings and humidity. Three Musketeers is manufactured by producing a highly aerated chocolate-flavored nougat center, forming it into a continuous slab, cutting it into bars, enrobing those bars in tempered chocolate, then cooling and wrapping while density and coating thickness remain tightly controlled. The defining step is the aeration system, because the bar's texture depends on holding a large volume of fine bubbles inside a stable sugar and fat matrix. The process, therefore, starts by building two streams that can be combined without collapsing air cells. One stream is a cooked syrup with a precise solids level. The other stream is a foamed phase that carries air at a controlled density. Syrup preparation begins with sugar and glucose syrup metering. Granulated sugar is screened to remove clumps and to keep dissolution predictable. Glucose syrup is held in jacketed tanks so it pumps at stable viscosity. Water is filtered and tempered because inlet temperature affects dissolving rate and cooker stability. The streams enter a dissolver, where agitation produces a clear solution. Strainers remove any undissolved grains because grains concede crystallization and create a gritty center. The clear syrup then enters a continuous cooker where heat drives off water. Many systems heat under pressure, so temperature can rise quickly without boiling in the coil. After the heating zone, the syrup may enter a flash stage where pressure drops and water vapor leaves rapidly. This trims moisture to the target. Moisture control here sets final nougat resilience. Too much moisture yields a soft center that can deform under cutters. Too little moisture yields a tough center that loses its light bite. While the syrup is being cooked, the aerated phase is prepared. A protein solution is mixed to a defined concentration and then sent to a continuous aerator. Airflow and rotor speed are controlled to create small bubbles and stable foam. Foam density is monitored continuously because it is the most direct indicator of final bar lightness. The foam must be stable enough to survive contact with hot syrup. It must also be fine enough to produce a smooth bite rather than large voids. The cooked syrup is cooled slightly to a controlled blending temperature and then combined with the foam in a continuous mixer. The mixer is designed to fold the streams together rather than whip. Folding distributes syrup through the foam while preserving the bubble structure. The syrup heat partially sets the protein films around bubbles and locks in the microcell network. Chocolate flavor is built into the nougat by adding cocoa components and sometimes chocolate liquor or cocoa powders at controlled points. These additions must be dispersed without deflating the foam. They can be introduced as fine powders, pre-blended with part of the syrup, or as a liquid chocolate. Stream introduced downstream of the highest shear zone. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be added in small doses to improve stability and control viscosity. Once mixed, the aerated nougat exits as a warm plastic mass with controlled density and viscosity. It is deposited onto a moving belt as a continuous slab. A spreader head lays down the slab at a defined width. Gauge rollers and leveling bars set thickness. Thickness control is critical because it determines bar mass and also affects cooling time. The slab enters a cooling tunnel where temperature drops in stages. Staged cooling prevents a hard skin from forming over a warm interior because that skin can crack and create weak planes during cutting. As the slab cools, the bubble structure stabilizes further. Fat begins to crystallize, and the nougat transitions from plastic to firm yet compressible. The target firmness is set, so the slab can be cut cleanly without smearing. If the slab is too warm, knives drag and deform edges. If too cold, the slab can fracture at the surface and create rough edges that show through the chocolate coat. Edge trimming is often used to remove uneven slab edges. Trims are collected as controlled rework. Rework must be managed carefully because aerated material behaves differently than fresh mix. Excess rework can shift density and bubble size distribution. The main slab then moves into lane cutting. Rotary knives slice the slab into long ropes of constant width. A crosscutter then slices the ropes into bar lengths. Cutter timing is synchronized with belt speed, so each bar length is consistent. The cut centers are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between bars. Transfer points are designed with low drops and soft transitions because aerated centers dent easily. Some lines include a brief pre-chill to firm the surface. Firmer surfaces accept chocolate more evenly and reduce deformation as the center passes through the curtain. Chocolate coating is prepared in a separate system where temper is the key variable. Chocolate is melted and filtered to remove unmelted particles. Tempering then creates stable seed crystals by controlled cooling and reheating. Working temperature is set so viscosity remains stable at the curtain. Viscosity controls the thickness of the coating and therefore the final chocolate to center ratio. Enrobing coats the bar with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a roller or a bath section that lays a consistent base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot at the base. Air knife settings are tuned to remove excess without exposing corners. Because the center is soft, air knife force is balanced so it does not deform the nougat under the coat. A pattern top can be applied by a stringer that drizzles thin chocolate lines over the wet surface. The drizzle must bond before the base coat fully sets. This requires a precise timing window between curtain exit and cooling tunnel entry. Pattern flow rate and nozzle spacing are synchronized with belt speed. Cooling tunnels set the chocolate. The first zone sets the surface quickly so the coating does not slump, and so the bar can be handled. Later zones cool more gradually to promote stable crystal growth and reduce bloom risk. Cooling must avoid condensation because moisture on chocolate creates sugar bloom and dullness. Tunnel humidity is controlled, and the bar exit temperature is set to support wrapping without scuffing. During cooling, the nougat center also equilibrates. The fat phase in the center continues crystallizing, and the bubble walls become more rigid. The center remains light and compressible, but it gains enough strength that handling pressure from wrappers does not deform it. The chocolate coat becomes a barrier that reduces moisture exchange and helps maintain texture over shelf life. Inspection follows cooling. Vision systems check for exposed edges and coating voids. Weight checks confirm bar mass and coating mass. Bars outside tolerance are diverted. Diverted product is handled as rework streams that are remelted for chocolate or reprocessed for nougat according to process rules. Wrapping begins once the bars reach a stable temperature. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are controlled, so seals are tight without shrinking film onto the bar. Film tension is controlled to avoid scuffing the chocolate surface. Print registration aligns graphics to bar position. Coating adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Twix bars are manufactured by producing a crisp biscuit finger, applying a controlled caramel layer, enrobing the assembled sticks in tempered chocolate, then cooling and wrapping while moisture and viscosity remain tightly controlled. The process begins with the biscuit line because the biscuit defines the bar geometry and the snap that must survive caramel deposition and chocolate coating. Flour is sieved to remove lumps and to standardize flow. Sugar is screened so crystal size is consistent and does not tear dough during mixing. Fat is conditioned to a plastic state so it blends evenly and limits gluten development. Leavening salts are weighed precisely because they determine porosity and bite strength. Water and any dairy liquids are tempered because dough temperature controls how cleanly it sheets and cuts. Mixing is designed to create a short dough with limited gluten. Fat and sugar are first blended to distribute fat and reduce dry friction. If a creaming step is used, it is controlled to avoid excessive air because too much air weakens biscuit and increases breakage during handling. Dry ingredients are then introduced and mixed only until the dough becomes cohesive. Minimal mixing limits gluten formation and preserves a tender, crisp structure rather than a tough one. Dough conditioning follows. The dough rests so moisture equilibrates and the dough relaxes. Relaxation prevents snapback during sheeting. Dough temperature is held in a narrow range, so fat stays plastic. Warm dough smears on rollers. Cold dough cracks at edges and produces rough cutouts. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through reduction rollers that gradually thin it. Gauge rollers set final thickness tightly because thickness drives bake time and final snap. Dusting flour can be applied sparingly to prevent sticking, but excess dust is avoided because it burns and creates specks. The sheet enters rotary cutting and docking. Rotary cutters punch long biscuit fingers. Docking pins create small holes through the dough. These holes vent steam during baking and prevent blistering and warping. The cut fingers transfer to an oven band. Scrap dough around the cutouts is lifted and recycled. Scrap ratio is controlled because repeated working increases gluten and changes dough behavior. Baking occurs in a tunnel oven with staged zones. Early zones set the shape as fat melts and moisture begins to leave. Leavening gases expand and create small pores. Mid-zones drive moisture down and develop a light golden color. Later zones finish drying so the biscuit reaches a low moisture endpoint. Moisture endpoint is critical because the biscuit must remain crisp under caramel and chocolate. If moisture remains too high, the biscuit will soften and lose snap. If moisture is too low, the biscuit becomes overly brittle and breaks during sandwiching and wrapping. After baking, the biscuit fingers exit the oven and enter cooling. Cooling stabilizes structure as fats resolidify. Cooling air is controlled and often dehumidified because dry biscuits can absorb moisture from humid air. The goal is a consistent exit temperature and moisture level. The cooled fingers are then aligned into lanes for caramel application. Caramel production runs in parallel because caramel must be depositable and stable. Sugar and glucose syrup are cooked with milk components to develop caramel flavor and reach an elastic solids endpoint. The cook drives off water until the caramel will hold shape at room temperature. Fat is added to smooth the caramel and reduce tack. The endpoint is set so the caramel bites cleanly without becoming glassy. Overcooked caramel becomes hard and can fracture when the bar is bitten. Undercooked caramel flows and smears in packaging. Caramel is cooled from cook temperature to a working temperature where viscosity is stable for deposition. It is held in jacketed tanks with gentle agitation to prevent skin formation. Pipes to the depositor are heated to prevent cold plugs. Viscosity is monitored indirectly by pressure and flow because a small temperature drift changes deposit weight and layer thickness. Caramel deposition applies a continuous layer onto the biscuit fingers. A slot depositor or multi-nozzle head lays caramel onto the moving biscuit lane. A leveling bar smooths the surface and sets thickness. Thickness must be uniform because it influences bite and chocolate coverage. If caramel is too thick, it can squeeze out under chocolate and create uneven edges. If too thin, the bar loses the intended caramel to biscuit balance. The biscuit temperature at deposition is controlled. Biscuit must be cool enough to remain crisp and to avoid melting caramel into the pores too deeply. It must not be so cold that caramel fails to bond. The line targets a temperature window where caramel adheres but does not soak. After deposition, the caramel-topped fingers pass through a cooling tunnel to set the caramel surface. Cooling must be staged so the surface firms without cracking. A firm surface is required before enrobing so caramel does not smear on belts. Once the caramel is set, the sticks are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfers minimize drop height because biscuit can crack and caramel can shear. The sticks may pass through a brief pre-chill to firm surfaces and improve chocolate flow behavior. Chocolate preparation is a separate stream where temper control is essential. Chocolate is melted and filtered. It is tempered to create stable cocoa butter seed crystals. Working temperature is set to maintain consistent viscosity. Viscosity determines how thick the chocolate curtain is and how much chocolate remains after air knife trimming. Enrobing coats the sticks in chocolate. A top curtain covers the caramel and sides. A bottoming system coats the underside, so the biscuit is sealed. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot thickness. Air knife settings must be tuned because too much air can expose corners, especially at biscuit edges. Too little air leaves thick feet that can crack during cooling. If a top pattern is required, it is applied immediately after the main curtain. A stringer deposits thin chocolate lines across the surface, while the base coat is still wet enough to bond. The stick then enters the cooling tunnel. Cooling sets the chocolate and locks the finished structure. The first zone sets the surface quickly to prevent slumping. Later zones cool gradually to promote stable crystal growth and reduce bloom risk. Cooling also reduces the internal temperature of caramel so it reaches its final elasticity. The exit temperature is set so the chocolate is hard enough for wrapping without scuffing. After cooling, the bars are inspected. Vision systems detect exposed biscuit corners and coating voids. Weight checks confirm portion control. Defective bars are rejected. Rework chocolate is remelted and returned upstream, while biscuit and caramel rework is handled separately because it carries moisture and texture changes. Wrapping begins with feeding bars into flow wrappers. Film is formed around each bar and sealed. Seal temperature and dwell are controlled so seals are strong without overheating the chocolate. Film tension is controlled to prevent scuffing. Print registration aligns graphics. Coding adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Mentos start as a controlled balance between dry crystals and warm syrup. The goal at the beginning is simple. Create a base that can be shaped without cracking, and then set it into a stable chew that will accept a hard shell. Sugar enters the line first, and it is treated as an engineered material rather than a sweetener. The crystals are screened so the size range is tight. That matters because the later mixing stage relies on predictable wetting. When crystal sizes vary too much, the small particles hydrate fast and the large particles stay dry. That creates weak zones that show up as gritty texture or uneven bite. In parallel, a glucose-based syrup is held at a steady temperature in jacketed tanks. The heat keeps the syrup flowing like a thick liquid instead of a slow gel. Pumps push it through filters and meters that smooth out pulsations. The entire point is to deliver the same flow every second. If the syrup surges, the candy core becomes soft. If it starves, the core becomes crumbly. Dry minor ingredients join through feeders that behave like precision valves. Texturizers such as starch are added to control stickiness during forming. Acidulants are added to tune brightness and to steer how the sugar phase behaves during conditioning. Very small additions are blended upstream so they do not land as streaks in the mass. The streams meet inside an enclosed mixer, where wetting is forced to happen quickly. Paddle elements sweep the walls and fold the mass through itself. The mixture passes through stages that look like dry sand at first and then like damp granules. As mixing continues, the granules begin to bind. The syrup coats the crystals and bridges them into a cohesive feed for the next machine. From the mixer, the material enters a continuous conditioner. This is where heat and shear begin the real transformation. The mass is kneaded while the temperature rises in controlled steps. Some of the sugar dissolves into the syrup phase. The remaining crystals stay intact and act like structural filler. That blend is what gives the final core its specific chew. Too much dissolution makes a rubbery bite. Too little dissolution makes a brittle bite. A vacuum section often follows to pull out trapped air. Air pockets are small, but they matter. They create internal voids that can collapse during coating. They also reduce density, which changes how pieces roll in later drums. When the air is removed, the mass becomes smoother and more uniform. Next comes forming, and this is where the process starts to look like candy rather than paste. The plasticized mass is pushed through a die to create a continuous rope. The rope has a defined diameter that matches the final piece width. A set of rollers or calibration guides controls the rope surface so it does not twist or flatten. The rope moves directly into a cutting unit that portions it into pellets. The cut timing is locked to belt speed, so every piece has the same length. The cut faces are still fresh and slightly tacky. That tack is useful because it allows the next step to round the shape without cracking the surface. The pellets enter a rounding stage where they tumble and roll against each other. The motion knocks off sharp edges and forces the surface to smooth. Friction warms the outer layer just enough to seal micro cracks. The goal is a dense core with a consistent geometry. That geometry is critical because the shell builds evenly only when each core rolls the same way. After shaping, the cores must be conditioned before coating. They travel through controlled air sections that adjust temperature and moisture. This step prevents shell defects later. If the core is too warm, the first shell layers dissolve and smear. If the core is too dry, the first layers do not bond well. Conditioning brings the cores to a stable state where the surface is firm yet receptive. When the cores reach coating, they enter large rotating pans or perforated drums. The core movement is constant and it is carefully tuned. The bed depth and rotation speed control collisions. Collisions must be strong enough to keep pieces separated. They must not be so strong that they chip the still forming shell. The shell is built in layers rather than one application. A coating solution is sprayed as a fine mist across the moving bed. Immediately after spraying, a dry powder is often dusted in. Airflow then removes moisture, so the layer sets before the next one arrives. This spray and dry cycle repeats many times. Each cycle adds only a thin film. Layering avoids cracks because stress is distributed gradually. At the start of coating, the syrup phase is more forgiving. It acts like an adhesive primer that locks onto the core surface. As cycles continue, the composition shifts toward harder, sugar-based layers. The process gradually moves from bonding to building. The shell thickens and becomes the structure that gives the candy its snap. Drying is not just about removing water. It is about controlling how crystals form. Fast drying can trap moisture inside and create a brittle outer skin. Slow drying can let the surface stay tacky and cause pieces to stick together. The airflow temperature and humidity are tuned, so crystallization happens evenly through the growing shell. As thickness increases, the process focuses on smoothness and roundness. The spray pattern is adjusted so no side gets more liquid than another. The drum motion is adjusted so pieces roll rather than slide. Rolling is what builds a uniform shell. Sliding creates flats and ridges that later show up as rough mouthfeel. Color and flavor can be introduced at specific points in the shell build. Early addition drives deeper penetration into the outer layers. Late addition keeps aroma closer to the surface. Timing is used as a control knob. It shapes how quickly the flavor is released when the candy is chewed. Once the shell has reached its target mass, the finish steps begin. A final smoothing phase uses lighter sprays and longer dry time. This reduces micro texture and tightens gloss. Then a polishing agent is applied in a thin film. The agent spreads under tumbling and fills tiny surface pores. The result is a clean shine and reduced friction, so pieces do not scuff in handling. The coated candy now needs final equilibration. It is held in bins or conditioning rooms where moisture equalizes between core and shell. This reduces internal stress. Without this step, the shell can craze. Crazing looks like fine cracks, and it can grow during storage. Quality checks happen along the line, but the main process signals are physical. Size distribution is checked because coating mass depends on surface area. Shell thickness is checked because it controls crunch and dissolution rate. Hardness is checked because it reflects both moisture and crystal structure. Surface inspection looks for chips and twins. Twins are two pieces stuck together during coating. When the product is cleared, it moves to packaging. The candy is conveyed to weighers that portion exact amounts. The flow properties matter here too. The polished shell helps the pieces slide and settle. Multi-head weighers use many small hoppers to assemble a target weight with minimal deviation. The measured portions drop into form-fill seal machines or cartoning systems depending on format. Film is formed into a tube and sealed. The drop is timed so pieces fall cleanly without crushing. Seals are made with controlled heat so the film closes without wrinkles. If cartons are used, the candy is fed into inner packs and then into outer sleeves. Nerds candy is built by turning concentrated flavored sugar syrup into a porous sheet, then fracturing that sheet into tiny irregular crystals, then sorting and finishing those crystals so each piece stays sharp and dry. Production starts with raw sugar management because particle size and purity drive how the syrup cooks. Granulated sugar is conveyed from bulk storage into day bins that feed the dissolving system. Screens remove oversized crystals and fines to keep dissolution predictable. Magnets and strainers protect downstream pumps and valves from metallic debris. A second carbohydrate stream is prepared to control viscosity and inhibit unwanted crystallization during cooking. Corn syrup is warmed in jacketed tanks until it reaches a stable pumping consistency. Flow meters and control valves keep corn syrup delivery steady across the run. Water is filtered and tempered so it enters mixing at a consistent temperature. Dry acids are staged in sealed hoppers so they remain free-flowing. Citric acid and malic acid are kept separate until late addition because acid affects inversion and color stability. Salt and buffering salts are staged in microfeeders when the recipe calls for them. Flavor concentrates are prepared in small tanks with controlled agitation so they stay homogeneous. Color solutions are diluted to a dosing range that avoids banding and streaking. The line splits early into two parallel syrup paths because Nerds typically pairs two flavors and two colors. Each path has its own dissolving and cooking controls, even if both share utilities. This separation lets each flavor reach its own target acid and aroma level without compromise. Sugar dissolution begins in a heated dissolver where sugar and water form a high solid slurry. Agitators sweep the vessel walls to prevent sugar crust. The slurry is heated until it becomes a clear solution. Inline strainers remove undissolved particles that would seed crystals too early. The solution flows to a balance tank that evens out feed rate to the cooker. Concentration is driven by a continuous cooker that raises temperature and removes water. Many lines use a coil or plate heat exchanger followed by a flash stage. The syrup enters under pressure so it can reach high temperature without boiling. The flash section drops pressure and releases water vapor in a controlled burst. This step tightens final moisture and improves consistency. Bricks and temperature are monitored constantly because small shifts change how the candy fractures later. A higher final moisture yields a tougher sheet that breaks into larger chunks. A lower final moisture yields a brittle sheet that shatters into dust. The target sits in a narrow window that supports clean fracture with limited fines. Corn syrup is injected at a controlled point to tune glass transition and reduce uncontrolled graining. The injection location matters because early addition changes cook behavior. Late addition can preserve more of the corn syrup function as a plasticizer. The syrup then passes through static mixers that eliminate streaking. Acid addition is handled carefully because acid can catalyze sucrose inversion during heat exposure. Many processes add acid after the hottest zone to limit inversion. The acid is metered as a solution to ensure rapid dispersion. Inline pH measurement is used in some lines as a confirmatory control. This stage sets the tart backbone that defines the flavor profile. Flavor and color are added after temperature is reduced to protect volatile compounds. A cooling loop drops syrup temperature to a range where aromas survive. Flavor oils are dosed through precision pumps into a turbulent region. Emulsifiers may be included, so oil-based flavors stay evenly distributed. Color is injected with high shear mixing, so each path produces uniform hue. The two flavored syrups now need to become solid candy in a form that can be fractured. One common approach is slab casting or film casting onto a cooled surface. The syrup is deposited as a thin ribbon onto a moving stainless belt. Belt speed and deposit rate set film thickness. Cooling plates beneath the belt pull heat out rapidly and evenly. As the film cools, it becomes a glassy sheet rather than a soft mass. Rapid cooling prevents large crystals from forming. The goal is an amorphous structure with controlled microcrystallization later. The sheet is guided through a cooling tunnel where air temperature and velocity are controlled. Surface moisture is kept low, so the sheet does not pick up tack. Some processes encourage controlled graining after initial set. This can be done by seeding or by mechanical working. Light agitation or flexing creates internal stress sites that guide fracture. The sheet may pass through a scoring station that introduces shallow grooves. Grooves create predictable breakpoints and reduce random oversized lumps. Once the sheet reaches a target, brittleness, it is released from the belt. A scraper blade lifts the sheet edge and directs it into a breaker. The breaker uses toothed rollers or oscillating bars to crack the sheet into pieces. The first break aims for chips that are still larger than the final candy size. This staged reduction avoids excessive dust creation. The chips move into a milling and crushing system that creates the nerd's granule size. A common setup uses roll crushers that apply compressive force. Roll gap controls the size distribution and also controls the amount of fines. Too tight a gap makes powder and reduces yield. Too wide a gap leaves chunks that do not feel like nerds. After roll crushing, the material enters a vibrating screen deck. Screens separate into multiple fractions in one pass. The target fraction is routed forward as product stream. Oversize is returned to the crusher for another pass. Fines are collected as a separate stream for rework or controlled reuse. The system is tuned to make irregular shapes rather than uniform spheres. Irregular shapes create the characteristic crunchy texture. The fracture surfaces must remain sharp and dry. Rounded surfaces would suggest coating that is too heavy or milling that is too aggressive. Because nerds often includes two flavors. In one pack, the line must keep colors separated until final blending. Each flavor color runs through its own crushing and screening loop. This prevents color contamination in recycle streams. It also allows each flavor to use its own target brittleness. Some flavors require slightly different moisture to break cleanly. Once each color is sized, it moves into conditioning bins. Conditioning allows moisture gradients to equalize inside each granule. Equalization reduces later caking in storage. It also stabilizes crunch by keeping the candy in a glassy state. Airflow in these bins is controlled to prevent humidity pickup. At this stage, the candy may receive a very light finishing step to improve flow. A tiny amount of anti-caking agent can be applied as a dry dust. The goal is to reduce surface stick points without changing texture. Application is done in a tumbler where powder distribution becomes uniform. Excess powder is removed by aspiration, so the finish remains minimal. Some formats use an additional micro-coating for color stability or acid placement. This can be done by misting a dilute syrup and then drying quickly. The mist acts as a binder for a fine acid layer or a color adjust layer. Drying must be fast so the granules do not fuse together. The micro-coating is kept thin to avoid rounding edges. If the recipe calls for a stronger sour hit, the acid can be partially surface loaded. Surface loading is done after sizing so the acid stays near the exterior. This approach changes perception because acid dissolves immediately. It also requires careful humidity control because acids can pull moisture. Granules are then blended to match the intended mix ratio. A gravimetric. Blending system meters each color stream. The blender uses gentle paddles or ribbon elements that avoid crushing. The objective is homogeneous distribution without generating new fines. Sampling at the blender outlet confirms color ratio across time. Transfer to packaging requires stable flow behavior. Granules can bridge if humidity rises or if fines increase. Hoppers are designed with steep walls and vibration options. Feed screws or vibratory feeders deliver candy into multi-head weighers. Weighers build target weights by combining small hopper dumps. Packaging format changes the final handling steps. In small boxes, the granules drop into cartons through a funnel system. Carton fill height is controlled to avoid crushing at the edges. In bag formats, the candy drops into a forming tube and then into sealed film. Seal timing is synchronized with the drop to keep granules out of seal areas. Some products use dual chamber packaging that keeps flavors separated until pouring. Dual chamber designs require two parallel weigh and fill lanes. Each lane fills its own side of the package. A split forming collar shapes the film into two channels. Seals create a central divider that remains intact. For mixed packs that combine two flavors in one cavity, the blender feeds a single weigher. The weigher controls portion size and drop accuracy. Drop height is minimized to reduce fragmentation. Chutes are designed with low friction surfaces to prevent hang-ups. Coding and inspection happen after sealing and closure. Vision systems can verify fill presence and detect seal contamination. Weight checks confirm package mass within tolerance. Reject systems remove outliers without stopping the line. Finished units are then collated into cases. Case packing is designed to limit vibration that could create dust. Cartons or bags are grouped and then dropped into corrugated cases. Cases are closed and sealed with tape or adhesive. Pallet patterns are chosen to reduce compression on lower layers. Skittles candy is made by building a chewy flavored center and then growing a crisp sugar shell that carries color and gloss. The process is a long chain of controlled transformations. It begins with dry powders and syrups that are treated like engineering feedstocks. It ends with uniformly sized pellets that flow through packaging equipment without sticking. The first stage is ingredient staging and metering. Granulated sugar is unloaded into silos and routed through screens that narrow the crystal size range. Consistent crystal size keeps dissolution predictable during cooking. Glucose syrup or corn syrup is held in heated tanks so it can be pumped at a stable flow rate. Water is filtered and tempered so it enters the system at a repeatable temperature. Minor ingredients are staged in sealed bins and then moved to microfeeders. These microfeeders meter acids and salts and functional powders with high precision. The center of a Skittles piece starts as a cooked candy base that will later be plasticized into a chew. Sugar and water first meet in a dissolving system that prevents dry clumps. Agitators create a strong vortex and pull crystals into solution. Heat raises the mixture to speed dissolution while avoiding localized scorching. The goal is a clear syrup with no undissolved grains. Inline strainers remove stray solids that could seed crystals later. The syrup then flows into a balance tank that smooths out any upstream fluctuations. From the balance tank, the syrup feeds a continuous cooker. The cooker raises temperature quickly to drive off water and concentrate solids. Many lines use pressurized heating, so the syrup can reach high temperature without boiling in the coil. After heating the syrup, enters a flash stage that drops pressure. Water vapor leaves instantly and pulls heat out at the same time. This step locks in final solids content and sets the base viscosity for the next stages. Solids content is tracked constantly because it affects chew texture and forming behavior. If moisture is too high, the centers stay soft and can deform during shell building. If moisture is too low, the centers become brittle and can crack under tumbling loads. Temperature is controlled with tight limits because viscosity changes rapidly with heat. Flow meters and control valves keep feed rate steady because residence time in the cooker must remain stable. After concentration, the hot syrup is cooled to a controlled temperature before sensitive ingredients are added. Cooling happens in a scraped surface exchanger or a plate heat exchanger. Scraped surfaces are used when viscosity is high and fouling risk increases. The cooled syrup enters a mixing manifold where functional additions are injected. Acids are added at this stage to manage flavor brightness and to set the target pH. Adding acid after the hottest zone reduces unwanted sucrose inversion. Flavor addition is handled as a separate system because flavors can be volatile and unevenly dispersing. Oil-based flavors are prepared as emulsions or are blended with carriers. Water-soluble flavors are diluted to a pumpable concentration. Both are dosed through metering pumps into a turbulent section of the stream. Static mixers fold the flow repeatedly to eliminate streaks. The objective is to make every portion of the candy base taste identical within a batch. Color is not usually placed in the center for a classic Skittles style. The center can remain neutral or lightly tinted depending on product type. This choice keeps the center stable and lets the shell carry the signature color identity. Even when the center is neutral, it must still be consistent in density and moisture. That consistency keeps shell growth uniform and prevents weak adhesion areas. The cooked and flavored mass now moves into a forming system. At this point, the material behaves like a thick plastic melt. It must be shaped into small pieces that will become the final candy cores. Extrusion is a common forming method for this kind of center. The mass is pushed through a die plate to create multiple ropes at once. Each rope has a controlled diameter that matches the planned final piece size after shell growth. As the ropes exit the die, they are cut into pellets. Cutting uses rotating knives or wire cutters synchronized to line speed. The cut length defines the initial core mass. Tight control is critical because shell thickness is added on top of the core. If core mass varies, then final piece mass varies, even if shell growth is perfect. The freshly cut pellets are soft and tacky. They must be conditioned quickly so they do not fuse together. Pellets transfer to a preconditioning conveyor or a cooling drum. Cooling air removes surface heat and firms the outer layer. The cooling profile is chosen to avoid a hard skin with a soft interior. A hard skin can crack during tumbling and expose a sticky interior. A uniform set keeps the pellet resilient during handling. The pellets may pass through a light dusting stage that prevents sticking. The dust is minimal and it is chosen to avoid changing flavor. Shaping continues with rounding. Pellets tumble in a rotating drum where they collide and roll. The motion rounds edges and smooths cut faces. Friction and gentle compression help the surface seal. The goal is a compact core with a slightly elastic bite. This elastic bite is what defines the chew under the later crisp shell. Rounding also improves how pieces roll in coating pans. Uniform rolling produces uniform shell thickness. After rounding, the cores undergo a rest stage. Rest allows moisture and temperature to equilibrate through the core. This reduces gradients that can cause deformation later. The cores move through conditioning bins with controlled airflow. Air temperature and humidity are adjusted so the core surface becomes dry enough for coating adhesion without becoming brittle. Moisture content is measured or inferred from process correlations. The process aims to keep the core in a stable glassy or rubbery state depending on formulation. Now the line transitions into shell building. Shell building is where Skittles develops its hard, crunchy outer layer. The cores enter large rotating coating pans or perforated coating drums. Rotation makes the bed of cores circulate in a continuous wave. Cores climb and then slide or roll down the moving bed. That rolling action exposes all surfaces to spray and to drying air. Shell growth happens in cycles. Each cycle applies a thin layer of syrup and then removes water to crystallize that layer. A spray system atomizes a sugar solution into a fine mist. Droplets land on moving cores and form a wet film. Almost immediately, dry air flows through the bed to evaporate water. As water leaves, the dissolved sugar crystallizes and locks into a solid layer. The drum continues rotating, so pieces do not stick to each other while wet. Nutella biscuits manufacturing begins with production of the biscuit shell using a rotary molding and baking process. The biscuit dough is prepared by blending wheat flour with vegetable fats and powdered sugar inside a continuous horizontal mixer. The mixer operates at fixed low speed to prevent gluten development while ensuring even dispersion of fat particles across the flour. Water is added near the end of the cycle to activate binding. The dough is mixed until it reaches a defined plasticity suitable for molding and is then discharged into a feeding hopper connected to the forming line. The rotary molder presses the dough into engraved cavities on a rotating drum. The cavities have an open bottom design to release formed biscuits onto a steel mesh conveyor belt. The upper roller applies pressure to ensure full cavity fill, while the scraper removes excess dough and reintroduces it into the system. Each molded shell includes a circular depression designed to receive the Nutella filling after baking. The unbaked shells are spaced at regular intervals on the conveyor to allow for controlled baking conditions. The biscuit shells are conveyed into a multi-zone tunnel oven for baking. The tunnel consists of top and bottom heating elements, independently controlled in each zone. The oven temperature rises gradually from 160 to 210 degrees Celsius across the length of the tunnel. The baking profile is optimized to achieve full moisture removal from the dough without causing expansion or deformation of the molded cavity. Residence time in the oven is calibrated to match dough moisture content and thickness. Shells exit the oven fully baked with crisp structure and low residual humidity. After baking, the biscuit shells are cooled using ambient air directed across multiple conveyors arranged in a serpentine path to reduce surface and internal temperatures evenly. Cooling is required to stabilize the biscuit structure and prepare the cavity for Nutella filling. The biscuits are held at rest until their surface temperature falls below 30 degrees Celsius to prevent filling separation. In parallel, the Nutella filling is prepared in a high-shear emulsification unit. Using sugar, skimmed milk powder, cocoa, hazelnut paste, and vegetable oils. The ingredients are pre-mixed in separate feeders and metered into a blending vessel. The vessel operates under vacuum to remove entrapped air and maintain smooth consistency. The filling is processed at controlled temperature of 40 to 45 degrees Celsius to keep the viscosity within a defined range suitable for extrusion. Once homogenized, the filling is pumped to a filling head fitted with multiple nozzles. The cooled biscuit shells are conveyed under the filling head where each cavity is aligned with a single nozzle. A volumetric piston system injects the Nutella filling into each cavity with precise volume control. The fill level is calibrated to rise just below the edge of the biscuit wall to allow sealing with the top biscuit layer. After filling, The open surface is inspected for overflow or inconsistency using machine vision systems that communicate with rejection gates for off-spec product. A second biscuit layer is prepared using a similar dough mixing and molding process, but with a flat profile and no cavity. These flat biscuits are baked and cooled on a parallel line. After cooling, they are conveyed to the sandwiching station, where they are aligned and placed on top of the filled biscuit shells. Robotic arms or mechanical pushers perform the alignment and placement. Each top biscuit is pressed gently to create full contact with the Nutella surface, ensuring mechanical bonding through surface tension of the fat-based filling. The sandwich biscuits enter a brief setting tunnel where cool air is applied to solidify the outer edges of the filling. This step reduces movement during handling and packaging. The biscuits exit the tunnel with the Nutella core enclosed between two baked shells. Completed Nutella biscuits are conveyed to a wrapping line. Each biscuit is separated by timing belts and transferred to a horizontal flow wrapping machine. Printed film is pulled from a roll and formed into a tube by a forming collar. The biscuit enters the tube, and the machine applies a longitudinal heat seal using rotating pressure rollers. End seals are created using heated sealing jaws that cut and close the wrapper simultaneously. Wrapped units are transferred to a grouping station where multiple biscuits are oriented into lanes and grouped for final packaging. Mechanical pushers move the groups into pre-formed trays or cartons, which are closed and sealed using hot melt glue. Cartons are held under compression for a fixed time to ensure glue adhesion before being moved to the final packing area. Each element of the Nutella biscuit structure is formed in distinct production zones that operate in parallel and converge during assembly. The biscuit shell relies on controlled dough plasticity, consistent cavity shaping, and uniform baking to maintain its geometry. The filling requires stable emulsification and thermal regulation to maintain deposition quality and shelf stability. Assembly depends on mechanical alignment, volumetric precision, and sealing reliability. Material flow through the plant is linear with dedicated conveyance systems connecting each station. Biscuit shells and tops are kept on separate synchronized lines to ensure timing consistency during sandwiching. The filling pump rate and nozzle actuation are matched to biscuit speed to maintain throughput. Each station includes real-time sensors to monitor dough consistency, bake color, biscuit thickness, fill weight, and seal integrity. These sensors feed data to a central programmable logic controller that adjusts line speed, pump rate, and heating elements based on tolerances. The manufacturing of Nutella biscuits depends entirely on coordinated dosing, shaping, heating, cooling, filling, sealing, and wrapping processes. Every stage transforms the materials physically by temperature or mechanical force, without the use of molding or batch processing beyond the initial dough and filling prep. All thermal zones are closed-loop systems with adjustable airflow and temperature feedback. Air velocity, humidity, and direction are optimized to control baking profiles and cooling rates. These variables determine final texture and filling retention. Filling viscosity is adjusted by temperature control and shear rate. The shear thinning nature of the filling allows fast deposition while maintaining form when static. Deposit shape is retained until enclosed by the top biscuit and set during the cooling phase. Final product dimensions are defined by the cavity shape of the rotary mold and the flatness of the sealing biscuit. Mechanical indexing ensures positional accuracy for every fill and seal. No lateral shift is tolerated at the sealing station. The top biscuit must be seated with uniform pressure to prevent leakage or deformation. This step is controlled by pneumatic actuators that apply force within a calibrated range to prevent structural damage to the shell. The flat biscuit must align concentrically with the base. All scrap or off-spec products are diverted to return belts for reprocessing or rejection. These include unfilled shells, misaligned sandwiches, overfilled units, and wrapping errors. Each rejection path is physically separated to maintain uninterrupted flow of conforming units. Finished wrapped units pass a final weight check and metal detection station before secondary packaging. Cartons are printed, coded, sealed, and stacked for dispatch. No rework is conducted beyond primary quality rejection zones. Oreo production starts with the preparation of the chocolate biscuit dough using a high-capacity continuous mixer. Dry ingredients including soft wheat, flour, sugar, cocoa powder, and leavening agents are first weighed and fed into the mixing chamber. A separate line introduces palm oil or shortening, which is preheated to maintain fluidity and evenly distributed across the dry blend. Water is added gradually to initiate dough formation while mixing paddles rotate at low speed to prevent overdevelopment of gluten. The process continues until the dough reaches uniform consistency with defined plasticity suited for rotary molding. The mixed dough is conveyed to the forming system via an auger feed mechanism. The dough enters the hopper of a rotary molder, equipped with engraved rollers that define the embossed biscuit design. As the dough passes through the rollers, it is pressed into the cavities with precise pressure and then released onto a wire mesh baking band by means of a stripping knife. Excess dough is scraped from the roller surface and returned to the feed hopper for reuse. Biscuits are formed in continuous rows and spaced evenly to allow thermal exposure during baking. The molded biscuit pieces are carried into a multi-zone tunnel oven. The baking process is divided into sequential zones where temperature and air velocity are independently controlled. The oven begins at a moderate heat to set biscuit shape and rises to higher temperatures to complete internal baking and develop surface color. The typical baking curve ranges from 160 to 220 degrees Celsius. Each biscuit remains in the oven for 6 to 9 minutes, depending on thickness and moisture content. The mesh band allows uniform exposure to heated air on all sides. After baking, the biscuits are discharged onto a cooling conveyor where ambient air is directed from above and below to bring the temperature down gradually. The biscuits move across multiple levels or loops of conveyors to extend cooling time without occupying additional floor space. Final biscuit temperature is reduced to below 30 degrees Celsius to ensure structural stability before sandwiching. Simultaneously, the creme filling is prepared in a separate emulsification line. The filling consists of icing sugar, hydrogenated vegetable oil, soy lecithin, and flavoring agents. Ingredients are loaded into a planetary mixer equipped with high-speed blades and jacketed walls. The sugar is ground and combined with oil under shear to produce a smooth, homogeneous, fat-based paste. Temperature is maintained between 35 and 40 degrees Celsius to control viscosity and ensure pumpability. Once mixed, the filling is transferred to a holding tank fitted with agitators to prevent settling or phase separation. The cooled biscuits are conveyed into the sandwiching station in a synchronized line. They are separated into top and bottom rows using mechanical diverters. The bottom biscuits move directly under the filling depositor, while the top biscuits follow a delayed path to allow time for the filling application. The depositor contains multiple nozzles aligned with each lane of biscuits. Each nozzle dispenses a fixed volume of cream using a positive displacement piston pump. The deposit is placed at the center of each biscuit with consistent diameter and height. Top biscuits are aligned and placed onto the filled base biscuits by a pick and place mechanism. A servo-controlled arm picks the top halves and lowers them precisely onto the creme layer. The contact pressure is adjusted to spread the filling evenly without causing overflow. The result is a sandwich structure with a defined creme layer held between two embossed chocolate biscuits. Each finished sandwich is inspected for alignment and fill consistency using vision sensors and rejected automatically if outside tolerance. Sandwiched Oreos are then conveyed to the packaging section. The product flow is timed to match the entry speed of the horizontal flow wrapping machine. Wrapping film is unrolled and passed through a former to create a continuous tube. The Oreos enter the tube and are enclosed longitudinally using heated crimp rollers. Transverse end seals are applied using rotating sealing jaws that cut and seal each package simultaneously. Seal parameters are adjusted for film thickness and product temperature. The wrapped Oreos exit the machine in a sealed pillow pack configuration. Multiple wrapped packs are grouped into secondary packaging units using collection conveyors and counting gates. Depending on the product format, they may be stacked or aligned edge to edge and loaded into pre-formed cartons. Cartons are formed from flat blanks using folding arms and sealed with hot melt glue. Filled cartons are compressed briefly to ensure adhesive bond and discharged onto the final conveyor. Each line operates continuously and is monitored by sensors that track biscuit position, deposit weight, package seal integrity, and material usage. The entire process is controlled by a centralized PLC system that coordinates line speed, temperature settings, pump pressures, and mechanical alignment across all stages. Biscuit texture is determined by dough moisture content, oven temperature profile, and baking time. Creme consistency is controlled through oil phase properties, shear rate, and deposition temperature. Assembly quality is a function of alignment precision, deposit accuracy, and pressure applied during sandwiching. Packaging integrity depends on film properties, sealing jaw temperature, and dwell time. Throughout Oreo production, no stage is batch-based beyond initial mixing. Dough and creme preparation feed into continuous mechanical systems that deposit, shape, bake, cool, fill, and wrap in a single linear sequence. Ingredient transformation is physical through heating, mixing, and compression. Structural integrity is achieved by thermal setting in the oven and mechanical bonding during sandwiching. The shape and weight of each Oreo are determined by the engraved mold cavities and the metered deposit volume. The embossed pattern is preserved by controlled dough texture and low expansion during baking. Biscuit brittleness is managed by adjusting water content and baking duration. Fill height is maintained by calibrating piston stroke length and pump cycle frequency. Every motion in the line contributes to dimensional uniformity and output consistency. Dough movement is regulated by roller speed and auger feed rate. Biscuit placement is defined by indexing and lane spacing. Creme application depends on nozzle diameter and internal deposit pressure. Sandwich closure requires precise Z-axis movement and timed application force. The rotary molding drum is cleaned automatically using scraper blades and air jets between production runs. Dough formulation is adjusted in real time based on humidity and flour batch variation. Viscosity of the creme filling is monitored using inline viscometers that signal temperature adjustments in the holding tank jacket. Oven parameters are logged continuously and used to regulate the baking curve. The production of Oreo cookies involves multiple heat and shear-based unit operations that alter physical properties without any fermentation or leavening beyond minor chemical agents. All dimensions are mechanically imposed and retained by careful control of thermal transitions and compression events. No rework is introduced into the sandwiching process. Only biscuits that meet shape, color, and thickness criteria are accepted. Filling rejects are filtered back into the holding tank through a return line. Packaging errors are removed before sealing to prevent final product contamination. The system is designed to maintain flow and reject outliers without stopping. The final Oreo structure consists of 2 rigid outer shells and 1 malleable creme layer. The shells resist deformation under handling. The creme adheres without fluid migration. Moisture barrier properties are maintained by the biscuit's low water activity and the hydrophobic nature of the fat-based filling. Nutter butter cookie production begins with the preparation of the peanut-flavored dough. Dry base materials are loaded into a large capacity horizontal mixer through automated dosing systems. These materials include soft wheat flour, granulated sugar, dextrose, baking soda, salt, and peanut flour. Separately, hydrogenated vegetable oil and peanut butter are preheated in jacketed holding tanks to reach a flowable state. The fats are pumped into the mixer and distributed over the dry mix, while the paddles rotate at low speed. Water is then injected into the chamber through spray nozzles to activate hydration without overdeveloping gluten. Dough temperature is maintained between 18 and 22 degrees Celsius. The dough is mixed until a target plasticity is achieved, ensuring it can be molded without sticking or tearing. Once complete, the dough exits the mixer via a discharge chute and is conveyed to a dough feed hopper mounted above a rotary molder. The molder is equipped with engraved rollers featuring the signature peanut shell pattern and split mold design that will define the top and bottom cookie pieces of the Nutter Butter sandwich. As the dough is fed into the rotary molder, the engraved drum compresses and shapes the dough into uniform cookie halves. A fixed scraper blade removes excess dough from the roller's surface, while a vacuum-assisted mechanism ensures accurate demolding from the cavities. Formed cookies are transferred onto a wire mesh conveyor belt that transports them through a continuous tunnel oven. Excess dough is rerouted via a return auger and refed into the forming system. The tunnel oven is divided into sequential thermal zones with independent temperature control. The initial zone sets the cookie shape at approximately 160 degrees Celsius. The intermediate zones raise temperature to 200 degrees Celsius to drive off internal moisture. The final zone applies finishing heat at 220 degrees Celsius to develop the surface texture and light browning. Airflow direction and volume are adjusted separately for top and bottom heating across all zones. The wire mesh belt permits full convection exposure around each cookie piece. Total baking time ranges from 6 to 9 minutes depending on dough moisture, product thickness, and belt speed. During baking, moisture content is reduced from around 18% to below 2%. The cookies exit the oven fully formed and structurally rigid. They are conveyed to an ambient cooling system composed of multi-tiered belts with forced air circulation. Cookies must reach below 30 degrees Celsius before proceeding to filling. While the cookies cool, the peanut butter creme filling is produced in a separate, continuous emulsification system. The formulation includes icing sugar, hydrogenated vegetable oil, roasted peanut paste, salt, and emulsifiers such as mono and diglycerides. The ingredients are metered into a vacuum mixer fitted with high-speed rotating blades. The mixer maintains low pressure to prevent air incorporation, while the fat and sugar blend into a smooth paste. Product temperature is held between 38 degrees Celsius and 42 degrees Celsius to control viscosity and ensure deposit stability. The filling mass is pumped from the mixer into a stainless steel holding tank equipped with a slow agitator to maintain consistency. From there, the creme is fed through a positive displacement pump into a volumetric depositor that sits above the sandwiching conveyor. Cooled cookie halves are divided into bottom and top rows using a mechanical separator with indexed belts. The bottom halves are aligned and conveyed beneath the depositor. Each nozzle in the depositor corresponds to one cookie lane. As each cookie passes below, a metered quantity of peanut creme is dispensed onto the center of the bottom cookie surface. The deposit rate is synchronized with belt speed to maintain consistent fill weight and location. Top cookie pieces are then aligned with their corresponding filled bottom halves using a mechanical alignment rail. A pusher bar or servo-driven actuator lowers each top cookie onto the filling. The applied pressure is controlled to spread the filling to the desired diameter without squeezing it beyond the edge. The resulting sandwich maintains clean fill lines and full bonding across the contact surface. Assembled Nutter Butter sandwiches are conveyed through a short resting belt to allow any residual filling movement to stabilize. From there, they move into the packaging system. The first packaging stage consists of a flow wrapping machine fed by a timing belt that spaces cookies at fixed intervals. Wrapping film is unwound from large rolls and formed into a tube around the cookies using a forming collar. The longitudinal seam of the wrapper is sealed by heated crimp rollers, while the ends are cut and sealed by rotary jaws. Temperature and dwell time of the sealing jaws are set based on film thickness and line speed. The wrapped cookies exit the flow wrapper as individual units or twin packs depending on the product variant. Wrapped units are conveyed to a grouping system where multiple cookies are collected and inserted into multi-pack cartons. Mechanical pushers or robotic pick-and-place arms load the cookies into pre-glued cartons. Cartons are sealed using hot melt adhesive applied by contact nozzles. Glue setting is ensured by compression flaps and a short dwell section. The cartons are then labeled, coded, and discharged to case packing. Throughout the process, all movements are continuous and synchronized. Dough feed, forming, baking, cooling, creme preparation, depositing, sandwiching, and wrapping occur without manual intervention or batch holding. Each station is linked to upstream and downstream processes by belt conveyors, sensor arrays, and real-time control systems. The final texture of the Nutter Butter cookie shell depends on dough fat content, moisture level, forming pressure, and thermal profile. The filling spread and adhesion characteristics are governed by shear during mixing, fat phase structure, and filling temperature at deposition. The sandwiching step relies on timing and vertical alignment accuracy to avoid rotation or breakage. Rework is minimized through inline inspection at multiple points. Cookies with incomplete molding, overbake, off-center filling, or misalignment are removed by air rejection systems or diverted for grinding and remelting. Only fully conformed products proceed to final packaging. The design of the peanut shell shape is retained through rigid cavity molding, low dough expansion, and short baking time. Each cavity in the mold drum is precision machined to micron level tolerances. The emboss pattern depth controls final surface visibility. The moisture balance in the dough ensures sharp edge retention and minimal slumping during oven transit. The filling deposit pattern is a function of nozzle diameter, piston stroke length, deposit speed, and creme viscosity. The diameter of the final fill is determined by vertical pressure from the top cookie and the flow behavior of the fat matrix. The ratio between shell weight and filling weight is maintained within narrow limits to ensure structural integrity and mouthfeel. Line efficiency is governed by synchronization between forming rate, baking throughput, and filling capacity. Adjustments to belt speed, oven temperature, or depositor cycle timing propagate downstream. Any mismatch between stations can result in underbake, inconsistent fill, or packaging misfeeds. The mechanical layout of the Nutter Butter production line is linear and modular. Dough flows from mixer to molder. Biscuits flow from molder to oven. Creme flows from mixer to depositor. Sandwiches flow from depositor to wrapper. Each segment includes buffer zones to absorb variation and maintain steady output. Packaging formats can be switched by adjusting forming jaws, wrapping film feed width, and carton loader configuration. Line reconfiguration is managed through digital interfaces that adjust motion profiles, material flow paths, and spacing intervals. The final Nutter Butter product consists of 2 molded peanut-flavored cookies bonded with a central layer of smooth peanut butter creme. The top and bottom shells are symmetrical and embossed with the same pattern. The cream layer is centered and flush with the cookie edge. The finished unit exhibits uniform thickness, aligned sandwich halves, and sealed packaging with fixed weight. Each unit operation transforms the ingredients through shear, heat, pressure, cooling, or extrusion. No fermentation or chemical expansion occurs. All structural characteristics are mechanically imposed and thermally locked. The line operates at a continuous pace of thousands of cookies per hour. Consistency across units is maintained by regulating every input condition, from ingredient feed to forming pressure to deposit rate. All cookies follow the same linear path through the same physical conditions. The result is a uniform, mass-produced sandwich product with no variation in shape, weight, or filling distribution. Peanut butter production begins with the bulk intake of raw, shelled peanuts delivered in containers or silos. Peanuts are gravity-fed into hopper systems equipped with vibratory feeders that control the rate of flow into the cleaning section. Cleaning involves sequential mechanical separation units, including air classifiers, rotary drum screens, and gravity tables. Air classifiers remove lightweight debris using high-velocity airstreams. Rotary screens separate based on particle size, discarding small fragments, sticks, and foreign seeds. Gravity tables use differential vibration and airflow to isolate denser whole peanuts from lighter defective material. Cleaned peanuts are transferred via bucket elevators into temporary storage bins prior to roasting. Roasting is carried out in continuous belt roasters or rotary drum roasters depending on line capacity. Peanuts are conveyed in a single layer through a thermal tunnel with forced hot air. Drum roasters use direct heat combined with rotating tumbling action. Roasting temperature ranges from 160 degrees Cs to 180 degrees Cs, with residence times of 25 and 40 minutes. Moisture sensors at the exit point ensure target moisture reduction to below 2%. Roasting also develops flavor and reduces microbial load. Cooled air is forced across the roasted peanuts immediately upon exit. Cooling conveyors equipped with perforated belts and axial fans reduce peanut temperature to below 35 degrees C to prevent oil migration or condensation. Peanuts are held in cooled hoppers with agitation to prevent bridging before entering the blanching process. Blanching removes the outer skin and splits the peanuts. This is performed in two ways: dry blanching or water blanching. Dry blanching involves friction rollers that rub off the skins as peanuts pass through serrated cylinders. Water blanching involves immersion in hot water, followed by belt conveyors fitted with rubber rollers. In both methods, skin fragments are removed by aspiration or vacuum collection systems. Split peanuts pass through inspection belts or optical sorters to remove discolored, moldy, or damaged halves. High-speed cameras scan each peanut and trigger air jets to divert off-spec material. Sorted peanuts are collected in surge hoppers and metered into grinders. Peanut grinding is performed in two stages: primary size reduction and emulsification. The first stage uses a hammer mill or disc attrition mill. Peanuts are fed into a chamber with rotating blades or abrasive plates. The initial grind reduces particle size to around 300-500 microns. The paste is then pumped into a second stage colloid mill. The colloid mill performs high shear homogenization between a rotor and stator, reducing particle size to below 100 microns. Rotor speeds exceed 3,000 RPM, and the grinding gap is adjustable for texture control. The grinding process also generates frictional heat, raising product temperature to 60-80 degrees C, which reduces viscosity and facilitates emulsification. During the second stage grinding, or immediately afterward, stabilizing agents and additives are introduced. Common stabilizers include fully hydrogenated vegetable oils, such as rapeseed or cottonseed oil. These are pre-melted in jacketed tanks and dosed using heated transfer pumps. Stabilizer addition typically ranges from 1 to 2% by weight and is controlled with flow meters. For sweetened or flavored varieties, additional ingredients such as sugar, salt, molasses, or cocoa powder are added through powder feeders or liquid dosing pumps. These materials are pre-weighed and incorporated in line using dynamic mixers with static mixing elements or turbine blades to ensure rapid dispersion into the viscous peanut paste. After additive incorporation, the peanut butter undergoes a degassing phase. The hot paste is transferred to a vacuum chamber or degassing tank where air bubbles are removed. The system applies vacuum pressure between 0.7 and 0.9 bar while slowly agitating the product to avoid entrapping more air. This step improves texture and packaging stability. Degassed product flows into surge tanks equipped with slow-speed agitators and thermal jackets to maintain fluidity. Temperature is held between 55 to 65 degrees AS to facilitate downstream handling. Product is then directed toward the packaging line via sanitary lobe pumps, which provide high volume transfer without shear. Before filling, the peanut butter may be passed through a scraped surface heat exchanger to adjust temperature precisely. The system uses rotating scraper blades inside a jacketed tube to maintain heat transfer efficiency without fouling. Outlet temperature is held constant, typically 50-55 degrees Celsius, for optimal flow into containers. Packaging is performed on high-speed, servo-driven filling lines. Empty jars made of PAT or PP plastic are depalletized and placed onto the conveyor. Each jar passes through an ionized air rinser that removes particulate matter. Clean jars are indexed into a rotary filler with multi-nozzle heads. Volumetric piston fillers or mass flow filling systems dispense precise quantities of peanut butter into each jar. Fill levels are controlled within plus 0.5% tolerance. Nozzles are heated or jacketed to prevent clogging due to cooling product. Some systems use bottom-up filling to prevent air entrapment and surface voids. After filling, jars proceed to the capping station. Caps are sorted and aligned using centrifugal feeders or vibratory bowls, then applied and torqued by rotary chuck cappers. Torque sensors monitor seal integrity, and improperly sealed jars are rejected automatically. If induction sealing is required, a foil liner is placed inside the cap. After capping, jars pass under an induction sealer where a high-frequency electromagnetic field heats the foil, bonding it to the jar rim. The seal creates a hermetic barrier that prevents oxygen ingress and oil separation. Labeled jars move to a wraparound or pressure-sensitive labeling station. Labels are applied using servo-controlled applicators, and optical sensors verify alignment and barcode presence. Rejected units are diverted to inspection lanes. Coded printing systems, typically thermal inkjet or laser, apply batch numbers and date codes to the lid or shoulder of each jar. The print system is synchronized with the conveyor speed to ensure clear, consistent marking. Jars are grouped into sets using collation conveyors and loaded into corrugated cartons or shrink-wrap trays. Case packers use robotic arms or mechanical pushers. Sealed cases are labeled with logistic codes and moved to palletizers. Palletizing systems stack cases using programmed layer patterns. Slip sheets are added as needed, and completed pallets are stretch-wrapped with plastic film to stabilize the load for transport. Each pallet receives an RFID tag or barcode label for warehouse tracking. Throughout production, inline sensors monitor critical parameters. These include product temperature, flow rate, fill weight, torque, seal integrity, and label placement. Data is logged by the Central Manufacturing Execution System and linked to batch tracking systems for traceability. Process water used in cleaning and ingredient dissolution is stored separately and heated as needed. All process equipment is connected to CIP systems that circulate detergent and rinse solutions through pipes, tanks, pumps, and valves at scheduled intervals. Cleaning sequences are validated using conductivity, temperature, and flow sensors. Environmental conditions such as air, temperature, humidity, and particulate levels are regulated in processing areas using HVAC systems with HEPA filtration. Maintaining a controlled environment prevents moisture pickup by roasted peanuts and ensures consistent flow behavior of the peanut paste during grinding and filling. Roasting profiles are monitored using thermal sensors and data loggers. Temperature curves are logged and compared against reference curves to ensure even development across peanut batches. Real-time moisture analyzers positioned at the roaster exit verify dehydration targets. Particle size of the final peanut butter is measured using laser diffraction or sieving techniques. Target particle size is typically below 30 microns for smooth varieties and above 100 microns for crunchy variants. Crunchy peanut butter includes the addition of roasted peanut granules, which are prepared separately using coarse grinders and added post-homogenization under low shear to maintain particle integrity. Oil. Separation resistance is measured during quality control using centrifuge testing or accelerated shelf life studies. Stabilizer effectiveness is confirmed through oil migration testing at elevated temperatures over time. Nutella production begins with the individual preparation of its components: hazelnuts, sugar, cocoa powder, vegetable oil, skimmed milk powder, lecithin, and vanillin. Each raw material is handled separately in dedicated systems to ensure proper particle size, mixing compatibility, and thermal behavior before integration. Hazelnuts are received shelled and pre-cleaned. They are conveyed through pneumatic lines into vibratory feeders that regulate flow into pre-roasting storage silos. From these silos, hazelnuts are metered into a continuous roasting system. Roasting occurs in horizontal convection tunnels or rotating cylindrical chambers, typically at 140 degrees, 160 degrees C for 20-25 minutes, depending on kernel moisture. The goal is to reach a final moisture level below 2% and to initiate flavor development. Post-roasting, nuts are directed into cooling drums or belt coolers. Forced ambient air lowers kernel temperature to below 30 degrees Celsius before further handling. The next step is blanching, where the brown skin is removed. This is done using mechanical friction rollers or pressurized steam exposure, depending on the desired throughput. Skin is separated by aspiration. The blanched nuts are then split and sorted by size via oscillating sieves, and undersized fragments are diverted. Cleaned, roasted hazelnuts are passed through a primary grinding phase using disc mills or pin mills to produce a coarse meal. This intermediate product is directed into a secondary grinding stage, often a ball mill or high-speed impact mill, which reduces particle size to a fine paste. Typical particle sizes are reduced to under 30 microns at this stage, producing a flowable hazelnut slurry with partial oil release. In parallel, sugar is handled separately. Granulated sugar is milled using air-classifying impact mills to reduce particle size and ensure dissolution in the final product. The resulting fine sugar powder is transferred pneumatically to dosing silos. A similar dry handling system is used for skimmed milk powder, which is fed into mixers via enclosed screw conveyors. Cocoa powder is stored in low humidity silos and transferred through sealed auger systems to prevent moisture absorption. It is typically defatted and pre-sifted to avoid clumps or oversized particles. All powdered ingredients, sugar, milk, and cocoa, are dry blended using horizontal ribbon blenders. These blenders operate at low speed to achieve uniform mixing without generating excess dust. The vegetable oil, primarily refined palm oil, is kept in liquid state in temperature-controlled storage tanks maintained at 45 to 50 degrees C. Oil is pumped through inline filters and metered into mixing systems via flow control valves. The oil acts as the continuous phase for the final emulsion and must be dosed with high consistency. All components are transferred into a batch mixing system. A stainless steel planetary mixer or a high viscosity processing vessel equipped with anchor agitators. The sequence starts with oil and hazelnut paste, followed by gradual incorporation of the powdered mix. Agitation is applied in stages, with high torque, low speed mixing used for initial wetting and medium speed agitation for full dispersion. Lecithin, added to control emulsion stability and flow, is stored in small heated tanks and introduced last. It is pre-mixed with a portion of the oil phase and dosed via peristaltic or gear pumps. Concentration is typically around 0.3% of the total mass. Vanillin, in synthetic form or as part of a flavoring premix, is injected at low concentrations and blended briefly under vacuum to prevent volatilization. The batch undergoes a refining stage using a 5-roll or 3-roll mill. The paste is pressed through steel rollers, reducing particle agglomerates and improving surface smoothness. The rollers operate at progressively higher speeds to create shear differentials, compressing solids and distributing fat evenly. Target final particle size is below 25 microns. After refining, the product is transferred to a conche, a jacketed horizontal mixer equipped with large mixing blades. The conching phase continues kneading at elevated temperatures of 50-60 degrees Celsius for 1 to 3 hours. This step enhances mouthfeel, disperses volatile compounds, and improves gloss by coating all particles with fat. Upon completion, the paste moves to a vacuum degassing tank where trapped air is removed. Vacuum is applied at 0.8 to 0.9 bar, while slow paddles maintain circulation. This step prevents air pockets in packaging and reduces oxidative degradation. The degassed product is homogenized through a low shear inline mixer to stabilize viscosity. The finished spread is transferred via jacketed pipelines to holding tanks prior to filling. These tanks are fitted with variable speed agitators and are temperature controlled at 40-45 degrees Celsius. A load cell system measures tank contents, coordinating flow to the packaging line. Transfer is performed with sanitary-grade rotary load pumps for accurate low-shear movement of viscous material. In the filling area, jars are supplied via unscramblers and aligned onto conveyors. They pass under vision cameras to confirm shape and cleanliness. Filling is done using servo-controlled piston fillers or mass flow metering systems. Fill nozzles are jacketed and temperature controlled to maintain flow characteristics. Fill volumes are typically accurate to within plus 0.5%. After filling, jars are sealed with aluminum foil using induction sealing. A liner is embedded inside each cap. When the cap is torqued onto the jar and passed under the induction head, an electromagnetic field heats the foil, bonding it to the jar rim. This creates an oxygen barrier and prevents oil migration. Caps are applied using rotary or inline capping machines with torque monitoring. If torque deviates from preset values, jars are rejected. Sealed jars move to the labeling station, where pressure-sensitive or shrink-wrap labels are applied. Labeling heads are adjusted for jar geometry and verified by optical sensors. Next, jars are passed under thermal inkjet printers, which apply date codes and batch identifiers. Printers are aligned with conveyor timing to ensure sharp, legible printing. Codes are verified by barcode readers or OCR systems. Rejected jars are diverted using pneumatic pushers. Labeled jars are grouped into sets using automated collation conveyors. Depending on destination, they may be packed into cardboard cartons or shrink-wrapped into trays. Cartoning machines erect boxes, load jars, and apply closure glue automatically. Case packers then arrange cartons into shipping cases with robotic arms. Shipping cases are sealed using hot melt glue applicators or tape dispensers and labeled with printed logistics data. The labeled cases are scanned, weighed, and conveyed to a palletizing station. Robotic palletizers stack cases according to optimized patterns, using vacuum or mechanical end effectors. Pallets are wrapped using rotary arm stretch wrappers. Film is tensioned to maintain structural integrity without distorting the cartons. Pallets are tagged with scannable barcodes or RFID labels for traceability. Throughout the entire production process, all operations are controlled and logged by a PLC-driven SCADA system. This includes ingredient dosing, thermal profiles, particle size measurements, fill volumes, torque levels, and packaging throughput. Parameters are displayed on HMI terminals and stored in batch records for traceability. Strawberry jam manufacturing begins with bulk delivery of strawberries in refrigerated containers. The fruit arrives pre-sorted or in raw form depending on source. Upon unloading, strawberries are tipped into stainless steel flume tanks where they are submerged in chilled water to reduce field heat and initiate washing. The strawberries are conveyed out of the wash tank using cleated food-grade belt elevators. A high-pressure spray bar located at the discharge point removes surface contaminants. Excess water is removed by air knives or centrifugal dewatering systems. Cleaned fruit is conveyed to the inspection station. At the inspection stage, strawberries pass over a slow-moving belt or roller table equipped with manual or optical sorters. Defective, underripe, or foreign objects are removed. High-resolution cameras with multispectral imaging may be used for automatic defect detection. Rejected items are separated using pneumatic actuators or diverters. Clean, sorted strawberries are directed to the hulling station. Hulling machines use rotating rubber fingers or mechanical plungers to remove the calyx and stem. The removed portions are separated by air aspiration. Hulled fruit is transferred to a temporary buffer hopper before size reduction. The hulling hopper meters strawberries into a dicing or pulping system. Dicing machines use oscillating blades to produce uniform fruit pieces. For homogeneous jam, fruit is passed through a finisher or pulper equipped with perforated screens and rotating paddles to produce a consistent puree. Screen aperture determines the level of texture in the final product. Pulpy fruit mass is weighed using inline load cells or flow meters and directed to a batching tank. In parallel, sugar is conveyed from silos or bulk bags into a dry blending unit. Sugar is sometimes preheated or dissolved in deionized water to create a syrup. This is controlled by mass flow regulation and prepared in jacketed mixing tanks equipped with agitators. Pectin is added either as a powder or as a pre-dispersed liquid. Powdered pectin is mixed with a portion of sugar to prevent clumping during hydration. The blend is fed into the batching tank via screw feeders or high shear dispersers. The type and concentration of pectin depend on the desired gel strength and fruit acidity. Citric acid is introduced to adjust pH, typically to the range of 3.1-3.4, which optimizes pectin gelation. Acid is dosed from a separate tank using peristaltic pumps monitored by inline pH probes. The exact amount is calculated based on the natural acidity of the strawberry pulp, which is measured per batch. In certain formulations, calcium salts may be added to activate low methoxyl pectins. These are metered in precise amounts using microdosing pumps. Water content is balanced by calculating the moisture level of incoming fruit and adjusting with deionized water or fruit juice concentrates. The full formulation, strawberry mass, sugar, pectin, acid, and optional additives, is transferred to a batch vacuum cooker. The cooking vessel is a steam-jacketed stainless steel kettle, often equipped with an anchor agitator and a central high-shear rotor for uniform heat transfer and reduced localized scorching. Cooking parameters are set to evaporate excess moisture, invert part of the sucrose, and activate pectin. The process is performed under partial vacuum to allow boiling at lower temperatures, preserving color and flavor while reducing thermal degradation. Typical target solids content for jam is 65-68 degree brix, measured with inline refractometers. During cooking, water vapor is extracted through a condenser system connected to the vacuum circuit. Condensate is collected and removed via gravity drains or vacuum traps. The jam mass is circulated continuously through the cooker using sanitary centrifugal pumps. This ensures uniform heating and prevents sedimentation of fruit particles. Once the desired bricks and viscosity are achieved, the batch is cooled through a scraped surface heat exchanger. This unit has a rotor with fixed blades that continuously remove product from the heat transfer surface, enabling rapid cooling while weighing, preventing fouling. Product temperature is reduced to below 85 degrees Celsius to prepare for filling. Deaeration is performed in-line or in a separate vacuum tank. This step removes entrained air bubbles introduced during cooking and agitation. Vacuum is maintained at approximately 0.8 bar, while slow agitation is applied to stabilize the product's density and texture. Optional flavoring agents or color corrections are added at this stage. Natural strawberry flavors or concentrated fruit essences are introduced through metering systems. Any added color is dispersed into a small portion of jam and blended thoroughly to prevent streaking. The final mixture is homogenized using low shear mixers to avoid foam generation. Finished jam is held in surge tanks equipped with level sensors, slow speed agitators, and thermal jackets to maintain flowability. Surge tanks are connected to the filling system via positive displacement pumps or rotary lobe pumps that handle viscous products with suspended solids. Glass jars or plastic containers are depalletized and transferred to the filling line using timing screws and indexing star wheels. Containers are first rinsed with filtered air or ionized air jets. Jars are checked by vision systems for cleanliness and structural integrity. Jam is filled hot, usually between 80-85 degrees Celsius, to enable vacuum sealing after capping. Filling is performed using piston fillers or mass flow-based servo systems. Fill volume is precisely controlled to match container dimensions and headspace requirements. Foaming is minimized by diving nozzles that dispense product near the base of the container. Immediately after filling, containers pass through a capping station. Metal twist-off caps with vacuum buttons or plastic snap-on lids are applied by mechanical torque heads. For metal closures, steam injection may be used just before capping to displace air and create a vacuum as the container cools. Capped jars move through an inverted holding tunnel or a rotary cooling system. Cooling is carried out using ambient air or chilled water sprays to bring the product below 40 °C. Gradual cooling prevents thermal shock to containers and promotes vacuum formation in sealed jars. Vacuum level is verified through cap button testing. Non-vacuum jars are automatically rejected. Labeling follows cooling. Jars are dried using air knives or infrared heaters before entering the labeler. Labels are applied using pressure-sensitive or hot melt glue systems, depending on the label substrate and application speed. Coded information such as production date, expiration, and batch number is printed using thermal inkjet or laser coders. Print location and clarity are verified by high-speed vision systems. Jars failing print quality checks are removed from the line. Labeled jars are grouped into cartons using robotic pick-and-place arms or mechanical collators. Cartons are formed from flat blanks, glued, and sealed using flap folders and glue guns. Carton integrity is checked by sensors measuring weight and dimensions. Cases are packed into shipping boxes or trays. Box formers erect corrugated cases, which are filled and sealed on a continuous motion line. Finished cases are conveyed to an automated palletizer, which stacks them in configured patterns for optimal stability. Pallets are conveyed to a stretch wrapping system where film is applied under tension. Each pallet is labeled with a scannable ID, linked to batch and traceability data. Wrapped pallets are moved to staging zones for distribution or temperature-controlled storage. Throughout the process, control systems monitor and log all variables. Programmable logic controllers manage dosing, cooking, filling, and packaging operations. Sensors measure temperature, flow, pressure, and viscosity. Human-machine interfaces provide operators with real-time control and alarms. Brix levels are verified at multiple points using digital inline refractometers. pH is measured with inline glass electrode probes. Final jam consistency is evaluated using rotational viscometers or Bostwick consistometers. Water activity meters confirm product stability. Chocolate is melted, filtered, and held at a stable temperature, so viscosity is constant. The key operation is tempering, which establishes a controlled population of stable cocoa butter crystals. Tempered chocolate behaves like a fluid at the depositor, but solidifies quickly into a glossy, firm structure. Tempering is maintained by staged cooling and reheating within a continuous unit, with sensors watching temperature and flow resistance as indirect signals of crystal content. The forming line starts with paper liners. Liners are denested and placed into cavities on a moving mold plate. Cavity fit is controlled because the liner must be supported to prevent wrinkling when chocolate is spun. Liner placement accuracy matters because a shifted liner creates thin shell walls on one side and thick walls on the other, which leads to breakage during demolding and uneven bite. Shell formation is done by depositing a metered shot of tempered chocolate into each lined cavity and then immediately shaping it into a cup. The shaping step is usually a spin or a combination of spin and vibration. Spinning forces chocolate up the liner walls and leaves a hollow center. Spin time and speed define wall thickness and rim height. If the spin is too aggressive, walls become too thin and crack later. If too gentle, the shell becomes heavy and reduces space for filling. Vibration during or after spinning helps remove bubbles and smooth the interior surface. The newly formed shells enter a brief cooling zone. This is not full hardening. It is a partial set that makes the shell self-supporting but still receptive to bonding with the filling. Cooling must be controlled because an overly cold shell can create poor adhesion and delamination. An overly warm shell can deform when filling is deposited and can create uneven rim geometry. Filling deposition is engineered to place a consistent puck inside the shell without contaminating the rim. The filling is delivered from conditioned hoppers to deposit heads that meter precise volumes. Depositing can be a single shot that forms a dome or a spiral that levels more evenly. The deposit height is controlled so there is clearance for the chocolate top. If filling touches the rim, it interferes with sealing and creates weak edges. Many lines use a light vibration or a short dwell to let the filling settle into a consistent profile, but the motion must be gentle because too much vibration can smear filling into the shell wall and create uneven thickness. Top sealing is created by depositing a second shot of tempered chocolate. The chocolate must flow outward enough to meet the shell rim and form a continuous bond. Deposit volume sets top thickness. Too thin a top can crack during handling. Too thick a top dominates bite and slows cooling. Some lines apply a short vibration after topping to level the surface and release trapped air. This vibration is tuned to avoid chocolate climbing the liner edge and creating flash. Once topped, the cups enter the main cooling tunnel. Cooling is staged because chocolate crystallization must be guided into a stable form. The first zone sets the surface quickly to prevent smearing and to lock the top shape. Subsequent zones cool more gradually so the entire chocolate mass crystallizes uniformly without internal stress. Exit temperature is chosen so the cups are rigid enough to demold and convey without scuffing. During cooling, the filling also stabilizes. Fat crystals within the peanut mixture continue forming and the filling becomes firmer and more brittle in its short structure. This is essential for the characteristic bite. If the filling remains too soft, it will squeeze under pressure and cause top separation. If it becomes too hard, it loses the expected crumble and becomes a dense block. Demolding releases the lined cups from the mold plate. Release depends on correct temper and correct cooling because the chocolate must contract slightly away from the cavity walls. Gentle ejectors or inversion steps drop the cups onto belts. Handling is kept low impact because rims can chip and liners can crease. Once on the belt, cups can pass through inspection stations. Vision checks can detect missing tops, off-center fills, and liner misplacement. Weight checks confirm dosing accuracy and flag missing deposits. Packaging is designed around preventing temperature rise and abrasion. Individual cups are often flow-wrapped. Wrapping film is formed around each cup and sealed with controlled heat and dwell time. Heat must be sufficient to seal film without warming the chocolate surface enough to mark. Film tension is controlled so it does not crush the cup. For multi-pack formats, cups are collated into trays or sleeves that prevent movement and protect rims. Cartoning then adds stiffness and stack strength. Case packing arranges cartons to reduce compression and minimize vibration that could crack chocolate edges. Skittles are manufactured by making a chewy center that behaves like a resilient pellet, then growing a hard sugar shell around that pellet in hundreds of small additions, then adding color and a final finish so every piece looks identical and moves cleanly through packaging. The center is engineered first as a thermoplastic candy rather than as a syrup. Sugar and glucose syrup are treated as structural ingredients that control glass transition and chew. Granulated sugar is screened so crystal size stays consistent and dissolution is predictable. Glucose syrup is held warm in jacketed tanks so it meters smoothly and does not pulse. Water is filtered and tempered because small temperature changes affect the cook profile. Acids and salts are staged as micro additions because they influence both flavor and how the cooked mass behaves during conditioning. A dissolving step makes a clear feed syrup. Sugar and water are mixed under heat with strong agitation until no grain remains. Any undissolved grain would later seed crystallization and create weak spots in the center. The clear syrup then enters a continuous cooker or batch cooker where it is concentrated to a high solids level. Heat input is rapid to minimize time at elevated temperature because long heat exposure darkens sugars and shifts texture. In many lines, the syrup is heated under pressure and then finished with a flash step that removes water quickly and tightens final moisture. Cook endpoint is chosen to produce a mass that can be shaped without sticking and without cracking. If moisture is too high, pellets deform and flatten during later tumbling. If moisture is too low, pellets become brittle and can fracture under coating impacts. The cooked base is therefore delivered to a cooling stage that drops temperature to a range suitable for adding sensitive components. Flavor for the center is not the same as the final flavor experience because much of Skittles' character is carried by shell and aroma at the surface. Even so, the center is commonly given a base flavor note and a consistent sweetness profile. Flavors are injected after the hottest zone to preserve volatiles. Acids may be split between center and shell strategy. A portion of acid can be added late to set a baseline tartness without weakening the center structure. Mixing downstream uses static mixers or low shear manifolds to avoid entraining air. The cooked mass then becomes a plastic dough and enters forming. Forming begins by pushing the mass through an extrusion head that produces ropes at a fixed diameter, or by delivering it directly to a pellet former, depending on equipment design. Rope diameter is a major variable because shell thickness is added on top, so the core size must stay tight to hit final piece size. A synchronized knife cuts the rope into pellets. Cut timing is locked to belt speed, so pellet mass stays consistent across the run. Fresh pellets have cut faces and a warm surface. They are transferred immediately to a rounding stage where they tumble and roll. Rolling knocks off sharp edges and produces the characteristic rounded shape that will coat evenly. This stage also seals micro cracks at the surface by gentle friction warming. Rounding is tuned to avoid smearing because smearing creates flats that later show as uneven shell thickness. After rounding, the cores go through conditioning. Conditioning is a controlled cooling and rest that stabilizes temperature and moisture through each core. The cores must be firm enough to withstand repeated coating cycles, but the surface must still accept initial shell adhesion. Conditioning airflow and temperature are set so surface surfaces are dry to the touch, while the interior retains the desired chew. Shell building is performed in rotating coating pans or perforated drums. The drum creates a rolling bed of cores that continuously cascades. Cascade behavior is controlled by fill level and rotation speed. A stable cascade ensures every core sees the same exposure to syrup spray and drying air. If the bed slides rather than rolls, pieces develop flat faces and shell becomes uneven. The first shell layers are engineered as a bonding bridge. A relatively light syrup is sprayed in short pulses. Droplet size is kept fine, so the film spreads thinly and evenly. Dry air immediately follows to evaporate water and begin crystallization. These early coats must set quickly to prevent pieces sticking together, and they must not add enough water to soften the core surface. Once the first layers lock on, bulk shell growth begins. A higher solid syrup is sprayed, and fine sugar is often dusted onto the wet surface. The dust absorbs moisture and accelerates set while increasing build rate. Airflow then dries the layer and forces crystallization. This spray, dust, and dry cycle is repeated many times. Each cycle adds a tiny increment of thickness, so stress remains low and cracks do not form. Drying is the most sensitive control in shell growth because it governs how crystals form within each layer. If drying is too fast, the surface can harden while moisture remains inside the layer, creating a trapped core that later pits or fractures. If drying is too slow, the surface stays tacky and pieces can twin. Twin formation is prevented by matching spray volume to drying capacity and maintaining continuous rolling so wet surfaces do not remain in contact. As thickness increases, the process shifts to smoothing. Powder addition is reduced, and the system relies more on thin syrup films that flow into micro valleys. Longer dry times then lock a smoother surface. Smoothness matters because it improves shine and prevents scuffing, and it provides a better substrate for printing. Color is applied as a sequence of thin coats rather than a single heavy dye layer. Color solutions are prepared to precise concentration and filtered so no particulates enter spray nozzles. Color is introduced when shell thickness is near target, so pigment remains close to the surface and looks bright. The drum receives a light color spray, then drying air sets it fully. Multiple passes build saturation evenly. Heavy color application would pool and create blotches, especially where shell microtexture is still present. Because Skittles are produced in multiple colors, runs are typically separated by color. Each color run uses its own color dosing and its own endpoint checks. Between colors, spray circuits are flushed to prevent cross tint. Shade is monitored by optical measurement on samples, and adjustments are made by changing pass count or concentration rather than by altering the underlying shell build. After color, clear finishing coats can be applied to improve durability and reduce rub-off. These coats are very light and followed by longer drying to reach a stable moisture endpoint. Moisture endpoint is critical because a slightly damp shell scuffs and sticks, while an overly dry shell can become brittle and chip under impact. The letter marking is applied near the end of finishing. Printing uses edible ink, transferred by a pad or similar contact method. Pieces are fed into a system that presents a stable face and applies the mark. Surface condition at this moment matters. The shell must be smooth and dry so the ink bonds and does not smear. A short drying stage follows, so the mark sets before pieces rub against each other. Polishing is the final surface operation. A very small amount of polishing agent is misted onto the tumbling pieces. The film spreads through contact and fills micropores, increasing gloss and reducing friction. Reduced friction helps pieces flow through packaging machines and reduces scuffing in bags. Polishing is controlled carefully because excess film can feel waxy and can interfere with print clarity. After polishing, the pieces are conditioned briefly to equalize moisture and temperature. Equalization reduces internal stress in the shell and improves resistance to fine cracking. Screening then removes fines, broken pieces, and twins that escaped earlier control. Size classification can be used to remove out-of-band pieces that would stand out in packs and behave differently in weighers. Packaging begins with gentle conveying into multi-head weighers. The pieces must flow freely without bridging. Hopper design and surface finish reduce sticking. The weigher selects combinations of small hopper dumps to hit target weight quickly. The portion drops into a form-fill seal machine, where film is formed into a tube and sealed above and below the product drop. Seal timing is set, so candies do not lodge in the seal zone. Clean seals are essential because moisture ingress softens shells and dulls gloss. For tube or carton formats, dosing can be by count or by volume, but the same requirement applies. Piece size distribution must be tight so count accuracy stays high, and so packs feel consistent. After filling, closures are applied and coating is printed. Packs are checked for weight and seal integrity, then case packed.